Think about a galaxy that is so old that it looks like the universe stopped 10 billion years ago. It's frozen in time, and a black hole that is so big it shouldn't even exist rules it. This is real life. It's NGC 1277, the Relic galaxy that lives in the Perseus Cluster. We'll find out in a few minutes how this small fossil goes against everything we know about how galaxies grow, why its huge black hole goes against the rules of cosmic balance, and what it can tell us about the first galaxies that ever lit up the universe. Discovery of NGC 1277. There are billions of galaxies in the night sky, and each one has its own past and structure. But every once in a while, scientists find one that doesn't seem to follow any of the rules. One of these strange things in the universe is NGC 1277. The story of the Perseus Cluster doesn't start with a big discovery. Instead, it starts with the careful, quiet work of scientists mapping out the galaxies in the group. At first glance, NGC 1277 didn't seem like much. It was just one of hundreds of small elliptical galaxies in one of the densest groups in the nearby universe. But at its center was something that would finally shake the foundations of the idea of how galaxies evolve. The earliest records of NGC 1277 date back more than a century. It was originally catalogued as part of the New General Catalogue, compiled in the late 1800s, which is why it bears the simple designation NGC 1277. Back then, astronomers could only note its fuzzy oval appearance through optical telescopes. No one could have guessed that this faint smudge contained one of the largest black holes ever measured. To them, it was just another galaxy in the Perseus Cluster, lying some 220 million light-years away from Earth. Fast forward to the 21st century. With more powerful instruments at their disposal, astronomers revisited galaxies like NGC 1277 to better understand their structure and star populations. In 2012, a team led by Remco van den Bosch of the Max Planck Institute for Astronomy used data from the William Herschel telescope in Spain, combined with follow-up observations from the Hubble Space Telescope and the Hobby-Eberly telescope in Texas, to study the dynamics of NGC 1277 stars. What they found stunned the astronomical community. The stars orbiting the galaxy's center were moving at such extreme velocities that the only explanation was the presence of a supermassive black hole of unimaginable size. Initial calculations placed this black hole at around 17 billion solar masses. To put that into perspective, the supermassive black hole at the center of our own Milky Way, Sagittarius A star, is a mere 4 million solar masses. This meant that NGC 1277's black hole was thousands of times larger than the one anchoring our galaxy, yet the host galaxy itself was much smaller than the Milky Way. That contradiction was the first sign that NGC 1277 was something very unusual. The announcement of this discovery sent shockwaves through astrophysics. Normally, galaxies and their central black holes follow well-established scaling laws. The bigger the galaxy, the bigger its black hole. But NGC 1277 shattered that rule. Its black hole accounted for an astounding percentage of the galaxy's total mass, far more than what was thought possible. Newspapers and science outlets quickly jumped on the story, dubbing it the galaxy that shouldn't exist. At the time, some people didn't believe the readings were accurate. Could the speeds of the stars have been read wrong? Was it possible that the tools on the camera had made mistakes? Astronomers brought in more tools to help them answer these questions. Hubble's high-resolution pictures proved that the galaxy is very compact. An integral field spectroscopy from ground-based telescopes made a more accurate map of how the stars move. It was clear from all the results that NGC 1277 really did have an overmassive black hole, and it wasn't a coincidence. This was more than just a curiosity. It was a challenge to decades of theory. The prevailing view in astrophysics was that galaxies and black holes evolve together. As galaxies grow through mergers and star formation, their black holes grow in tandem, maintaining a fairly consistent ratio of mass. NGC 1277 didn't fit that pattern. Instead, It looked as if the black hole had grown extremely fast in the early universe, while the galaxy around it had stopped evolving billions of years ago. As the data poured in, astronomers realized they weren't just looking at an oddball galaxy, they were peering into a time capsule from the early universe. The stars of NGC 1277 were ancient, with ages estimated at more than 10 billion years. There was no sign of recent star formation, no cold gas to fuel new stellar nurseries, and no evidence that the galaxy had undergone major mergers in the past several billion years. In other words, NGC 1277 had remained largely unchanged since the universe was only a fraction of its current age. Location in the Perseus Cluster. Before we can figure out what NGC 1277 is all about, we need to know where it is in the universe. There are other galaxies out there, not just this one. Instead, it lives in the Perseus Cluster, which is one of the biggest and busiest places in our galaxy. This cluster is made up of more than 1,000 galaxies that are pulled together by gravity. It is about 220 million light-years from Earth. Astronomers see the Perseus Cluster as both a laboratory and a theater. It is a place where galaxies live, interact, and sometimes crash into each other, showing how the big events that have changed the universe have happened. The Perseus Cluster takes its name from the constellation Perseus, which can be seen in the northern sky during autumn and winter. Its heart is dominated by a giant central galaxy called NGC 1275, a luminous active galaxy with a ravenous black hole that blazes in radio and X-ray wavelengths. Around this dominant player, smaller galaxies orbit in a dense swarm, all held together by the immense gravitational pull of the cluster's dark matter halo. NGC 1277 is one of these smaller members, orbiting within the gravitational domain of the cluster's center, not far, at least on a cosmic scale, from NGC 1275 itself. Pinpointing NGC 1277's location reveals a lot about its survival. In such a crowded cluster, galaxies are constantly subjected to gravitational tugs, gas stripping, and even high-speed encounters with neighbors. Yet despite living in such a harsh environment, NGC 1277 appears remarkably untouched, almost as if it has been shielded from the violent processes that usually reshape galaxies. This is one of the key reasons why astronomers describe it as a relic. Most galaxies in clusters like Perseus undergo interactions that transform their structures, stir up new star formation, or strip away gas. NGC 1277, by contrast, sits quietly, almost invisible next to its flamboyant giant neighbor. Finding NGC 1277 in the Perseus cluster is not easy from Earth's point of view. A lot of galaxies can be seen merging in camera pictures because the cluster covers a large area of the sky. To tell NGC 1277 apart from the other galaxies in the area, you need to carefully measure its light spectrum. Astronomers can be sure that it is part of the cluster and not just a local or background galaxy by looking at how the bands of its light are stretched. This is called redshift. The fact that NGC 1277 has the same redshift signature as Perseus proves that it is a real part of the cluster's family. Its location is even more captivating because it is close to NGC 1275, which is the brightest galaxy in the cluster. It is known for the strands of gas that shoot out from its center, which were formed by jets from its active black hole. NGC 1275 is a monster in its own right. It almost seems strange to find a small relic galaxy like NGC 1277 in the same setting. One is a bright light of activity and growth, while the other is a frozen rock that hasn't changed much in 10 billion years. But they both circle in the same cluster and are affected by the same gravitational field. This gives scientists a unique chance to see how the galaxy has changed at two very different points in time. The Perseus cluster itself is more than just a collection of galaxies. It is also one of the brightest sources of X-rays in the sky. This glow comes from hot, intra-cluster gas heated to tens of millions of degrees, filling the space between galaxies. Any galaxy moving through this dense, hot medium experiences ram pressure stripping, a process that can strip away its cold gas, halting star formation. This environment likely played a role in NGC 1277's history, ensuring that once its initial burst of star formation ended, no new gas could replenish it. In this sense, the Perseus Cluster acted like a cosmic freezer, preserving NGC 1277 in its ancient state. Its connection to dark matter is another thing about where it is. Dark matter halos, which are huge, unseen objects that make up most of the mass of clusters like Perseus, control them. These halos hold galaxies like NGC 1277, and how they interact with the dark matter potential around them affects their ability to stay alive. Later studies of NGC 1277 showed that it has surprisingly little dark matter for a galaxy of its type, which made scientists even more confused. Being in the cluster could help explain some of this. The dark matter ring could have been stripped away by ram pressure stripping and gravity interactions, leaving behind a core that is bare and dense. Studying NGC 1277 within this cluster context also emphasizes its rarity. Out of thousands of galaxies in Perseus, very few resemble it. Most are either large, extended ellipticals or smaller gas-stripped remnants. NGC 1277, with its tightly packed stars and oversized black hole, stands out as an oddity. It seems to have followed a completely different evolutionary path than its neighbors. If Perseus is a bustling city of galaxies, then NGC 1277 is like an ancient building preserved in the middle of modern skyscrapers, a relic of a bygone era that somehow survived unchanged. Why it's called a relic galaxy. When it comes to science, words matter. When scientists call NGC 1277 a relic galaxy, they're not just giving it a cool name. They're referring to the fact that it's a frozen piece of history from when the universe was young. Before we can understand why this name is important, we need to take a step back and look at what a ghost galaxy is, and why NGC 1277 is such a great example of that type of galaxy. A relic galaxy is essentially a cosmic time capsule. Most galaxies, including the Milky Way, have spent billions of years evolving, growing through mergers and recycling gas into new generations of stars. But relic galaxies skipped those later stages of development. They formed quickly in the early universe, burned through their star-forming fuel, and then stopped evolving. Instead of growing into massive spirals or ellipticals, they froze in place, preserving their original structure and stellar populations from the dawn of cosmic history. They are sometimes called red nuggets because of their compact size, reddish color, and high density. It's clear that NGC 1277 is a red nugget. With ages ranging from 10 to 12 billion years, its stars are almost all very old, so they were formed not long after the Big Bang, about 2 billion years ago. Using spectroscopy, scientists have found no signs of younger stars, no infrared signs of stars still forming, and no gas stores that could be used to make more stars. To sum up, NGC 1277 started to form early and quickly, but then it stopped and would never start up again. Astronomers call it a ghost because it looks like it is frozen. One thing that makes ghost galaxies unique is how small they are. When we look at galaxies from a long time ago, galaxies with a high redshift, we see a group of small crowded ellipticals that were very common about 10 billion years ago. Over time, those galaxies got bigger by merging and adding to each other, turning into the bigger ellipticals we see today. The star NGC 1277 never grew that big. It stayed small and dense, just like its ancestors from the beginning of the universe. In this way, it's like finding a living dinosaur among modern birds. It's a reflection of how the world looked in the beginning, kept alive in the present. Another aspect of its relic nature is the complete absence of cold gas. Galaxies need cold molecular gas as raw material to form stars. Spiral galaxies, for example, contain vast clouds of hydrogen that constantly collapse into new generations of stars. But in NGC 1277, observations at radio and millimeter wavelengths show little to no cold gas. Without that fuel, Star formation has been impossible for billions of years. Its stellar populations are effectively sealed off, locked in the state they reached after their initial burst of formation. The Relic designation is also tied to its environment. As a member of the Perseus Cluster, NGC 1277 has spent billions of years bathed in hot intra-cluster gas. Any cold gas it might once have had would have been stripped away by the cluster's harsh conditions. While many galaxies in Perseus were reshaped by mergers and interactions, NGC 1277 appears to have escaped with its compact form intact. This environmental quirk helped freeze it in time, preserving it as a relic while others moved on. Its compactness and ancient stars also explain its reddish hue. Without new blue stars forming, the galaxy glows mainly with the light of older, redder stars. This gives it the characteristic appearance of a red nugget. The term may sound simple, but it encapsulates a profound truth. Galaxies like NGC 1277 were once the building blocks of the universe, and now they are almost extinct, with only a handful surviving to the present day. What makes NGC 1277 stand out among relics is the size of its central black hole. While other red nuggets also host large black holes, NGC 1277's is so dominant that it accounts for an unprecedented fraction of the galaxy's total mass. This makes it not just a relic, but an extreme example, a galaxy frozen at a stage where the black hole had already grown enormous, yet the galaxy itself never followed the normal path of expansion and mergers. That imbalance, preserved for over 10 billion years, is what makes NGC 1277 both a relic and an anomaly. The concept of relic galaxies is relatively new in astronomy, becoming clear only in the past 2 decades as telescopes grew powerful enough to peer deep into cosmic history. By comparing nearby galaxies to their ancient counterparts at high redshift, astronomers realized that a few survivors like NGC 1277 had managed to avoid the typical evolutionary processes. Each relic galaxy is therefore a goldmine of information about the early universe. By studying them, scientists can reconstruct what conditions were like during the peak of galaxy formation. Size and structure of NGC 1277. If you think of a galaxy with one of the biggest black holes ever found, you might picture something very big, like IC 1101 or one of the huge spiral galaxies that make up most galaxy groups. But NGC 1277 doesn't work that way. Even though it's very well known, the system is actually very small and tiny. One of the main things that amazed scientists about it was its small size matched with its huge central black hole. To really understand how strange it is, we need to look at its size, shape, and construction from the inside. NGC 1277 is classified as a compact elliptical galaxy. While the Milky Way spans about 100,000 light-years in diameter, NGC 1277 is only about 10,000 light-years across. That makes it roughly 10 times smaller than our home galaxy. Yet despite its small size, it is incredibly dense. Pack the stars of the Milky Way into a region 1/10 its size, and you begin to understand what kind of environment NGC 1277 represents. Its stellar population is crammed into a volume that creates a tightly bound high-gravity system. Its compact nature is tied to its history. In the early universe, galaxies known as red nuggets were common, small, dense, spheroid-shaped galaxies that formed quickly and then stopped evolving. Most of those nuggets later grew larger through mergers and accretion, puffing up into extended ellipticals. NGC 1277 never did. It retained its compactness, which is why astronomers refer to it as a relic galaxy. The preservation of its small, dense form provides a unique opportunity to study galaxy structure as it existed billions of years ago. The structure of NGC 1277 can be described in layers. At its heart lies the supermassive black hole, dominating everything around it. Encircling the black hole is a dense central bulge of stars, the spheroidal component that gives the galaxy its elliptical classification. Unlike spiral galaxies, which feature disks, spiral arms and bars, NGC 1277 is almost entirely bulge-dominated. Its shape is smooth and oval, with little sign of substructures like star-forming regions or dust lanes. In visible light, it appears as a luminous oval smudge, faint compared to the dazzling spirals we're used to seeing in space imagery. The very high number of stars in NGC 1277 is one of the things that makes its structure unique. Astronomers think that it has about 100 billion stars spread out over 10,000 light-years. In contrast, the Milky Way, which is 10 times as wide, has about 200–400 billion stars. In other words, NGC 1277 fits almost half of the stars in our galaxy into a very small space. As a result, the stars are very close together and are moving very quickly as they circle around the galaxy, which is being pulled by the gravity of both its mass and the huge black hole at its center. The compactness of NGC 1277 also means it lacks some of the features we associate with more normal ellipticals. Extended halos of stars are almost absent. There's no visible sign of recent merger scars, tidal streams, or diffuse outer envelopes. It looks stripped down, almost skeletal, compared to the more bloated ellipticals around it. This minimalism reinforces its relic status. It is what galaxies used to look like before billions of years of mergers reshaped them. Experts often say that NGC 1277 is like the core of a normal spiral galaxy, but without the rest of the galaxy's mass. There isn't much filler in it, just the core. That could be the reason why the black hole looks so big. The bulge and ring in bigger galaxies lower the black hole's mass share. Without those long structures, the black hole looks much bigger than the mass of all the stars put together in red. The rotation, or rather the lack of rotation, is another important part of its structure. Spectroscopic studies show that the stars in NGC 1277 are mostly pressure-supported, which means that their movements are not grouped into a rotating disk, but are rather random. This is another proof that it is an oval shape, and that it formed violently and quickly in the early universe. These pressure-supported systems are more common in galaxies that form quickly through big bursts of star formation and early crashes than in spiral disks, which rotate slowly and steadily. NGC 1277's shape is slightly elongated, with an axis ratio that makes it look like a flattened spheroid rather than a perfect sphere. But it is smooth, showing none of the chaotic features we would expect if it had undergone recent mergers. Its light distribution falls off sharply with radius, another indicator of its compactness. Photometric analyses confirm that its surface brightness profile is steep, meaning most of its stars are concentrated toward the center. Scientists have also made guesses about how it evolved based on its makeup. One idea is that NGC 1277 is what's left of a bigger galaxy whose outer layers were washed away by the tides interacting with other galaxies in the Perseus Cluster. If that's true, then what we see now could be the very core of a bigger system. This theory doesn't fully fit the facts, though. Its stellar populations are all very old, which suggests that stripping didn't reveal any new layers or start-star formation. The most common belief is that NGC 1277 was always small and never got bigger. Stellar population, ancient stars only. A lot of people say that galaxies are like star towns, full of different kinds of stars of all ages, colors, and sizes. Some are busy cities that are always giving birth to new stars in lively homes. Others are more like sleepy places, where only old people live. NGC 1277 is definitely in the second group. The vast majority of the stars in it were born billions of years ago, when the universe was still very young. This is the very definition of an old stellar population. Astronomers studying the light of NGC 1277 have been able to measure the ages of its stars with remarkable precision. Spectroscopic surveys indicate that the majority of its stellar population is between 10 and 12 billion years old. That means these stars formed just 3 billion years after the Big Bang, during an era when the first major galaxies were assembling. Since then, NGC 1277 has essentially closed up shop, forming no significant new stars. Its stellar city has been frozen in time, populated only by its original residents. This ancient population is revealed through the galaxy's color. Unlike star-forming galaxies, which shine with the blue light of young hot stars, NGC 1277 glows with a reddish hue. That red color is a hallmark of aging stars, cooler, longer-lived ones that dominate after the hot, short-lived blue giants burn out. Ultraviolet observations confirm the lack of new, massive stars, while infrared studies further highlight the dominance of old red giants. Together, these data paint a clear picture. NGC 1277 is a graveyard of stellar activity, its light powered by the remnants of a furious starburst that ended billions of years ago. How do we know it hasn't formed stars since then? One clue comes from the lack of cold gas. Star formation requires clouds of hydrogen and dust to collapse under gravity and ignite nuclear fusion. In galaxies like the Milky Way, these raw materials are abundant. But in NGC 1277, astronomers have detected almost none. Observations using radio telescopes, which can reveal cold hydrogen gas, return nearly empty results. Without fuel, the galaxy cannot spark new stellar births, leaving its population to age in place. Metallicity, or the number of elements heavier than hydrogen and helium, is another piece of proof. The stars in NGC 1277 have a lot of these metals, which means they formed quickly and intensely early in the past of the universe. When a lot of big stars come together and die quickly, they leave behind supernovae that add heavier elements to the area around them. As a result, there are more stars with higher metallicities than we would have thought if star formation had happened slowly over billions of years. It looks like the stars in NGC 1277 were formed by a cosmic flash fire. They burned hot and quickly, and then they were left to cool down without any more fuel being added. By studying galaxies like NGC 1277, astronomers gained direct insight into the conditions of the early universe. Most galaxies we see nearby have had complicated histories, mergers, interactions, and repeated bursts of star formation that erase their early fingerprints. But NGC 1277 has preserved those fingerprints. Its stars tell us about the density, composition, and dynamics of the universe when it was just a fraction of its current age. Another amazing thing is how regular the population of stars is. In many galaxies, stars of different ages live in different areas. For example, young blue stars are found in the spiral arms, while older redder stars are found in the center bulges. But in NGC 1277, the stars are all the same age, meaning they are all very old. This consistency supports the idea that it had one big explosion early on and then stopped. There were no more events to make the community more interesting. It's a picture of a single moment in the history of the universe that has been frozen for billions of years. The lack of young stars also has consequences for the galaxy's dynamics. Younger populations, especially massive O and B stars, often drive energetic winds and supernova explosions that stir up the interstellar medium. Without them, NGC 1277 is a quieter, more stable environment. Its internal motions are governed primarily by the gravitational pull of its dense stellar mass and, of course, the monster black hole at its center. In a sense, it is a galaxy on pause, its evolution stalled by the absence of fresh energy input. Some researchers have suggested that NGC 1277 could be one of the best examples of the red nugget galaxies that were common at high redshift. These compact, old, star-dominated galaxies were thought to be the seeds of modern-day ellipticals, but while most nuggets grew larger through mergers, NGC 1277 never did. Its survival as a compact relic means its stellar population offers a unique chance to compare nearby fossils with their ancient distant cousins. Evidence of no new star formation. One of the most important tests to see if NGC 1277 is really a remnant galaxy is to show that it hasn't made stars in billions of years. Galaxies usually go through bursts of activity where gas clouds collapse into bright new stars that keep the galaxy alive and well. NGC 1277 is not like that though. It has been idle for more than 10 billion years and hasn't made any new stars. One of the best signs that it is a fossil from the early world is that it shut down completely. The first line of evidence comes from its color. Astronomers use a tool known as the color magnitude diagram. The first line of evidence comes from its color. Astronomers use a tool known as the color magnitude diagram to study stellar populations. Star-forming galaxies, rich in hot, young stars, tend to appear blue in color, while galaxies that have stopped forming stars glow red. NGC 1277 is firmly in the red sequence, meaning it has a population dominated by older stars with no sign of the bright blue signatures that indicate ongoing star formation. Its light is almost entirely from long-lived red giants and ancient stars that have been shining since near the dawn of time. The search for gas is another important challenge. Dark, thick clouds of gas and dust are where stars are born. A galaxy can't make new stars without these things. Astronomers used radio and millimeter studies, especially those that looked for emissions from molecular hydrogen tracked by carbon monoxide, CO, to find out if NGC 1277 still has fuel. Cold gas can be found even in very faint forms using instruments like the IRAM 30-meter telescope and ALMA, Atacama Large Millimeter Submillimeter Array. How did they do? Not much at all. It looks like NGC 1277 doesn't have any of the cold gas stores that galaxies need to start making new stars. Complementary data from infrared surveys also back up this conclusion. In galaxies where new stars are forming, dust heated by young stars emits strongly in the infrared. Observations from Spitzer and Herschel space telescopes show no such emission in NGC 1277. The lack of warm dust is another indicator that no stellar nurseries are active inside the galaxy. Its environment is cold, sterile, and quiet. Researchers also use ultraviolet, UV light, to look for star formation. Young, huge stars emit a lot of UV rays as they burn extremely hot. This unique sign has been found in galaxies using tools such as Relics, Galaxy Evolution Explorer. NGC 1277 once more doesn't show any signs. Its spectrum is mostly made up of older, cooler stars, and the ultraviolet part is missing. In recent cosmic history, this proves that no hot, huge stars have formed there. The galaxy's environment within the Perseus Cluster reinforces this story. Clusters are filled with hot, X-ray emitting plasma that permeates the space between galaxies. Any cold gas that NGC 1277 might once have had would have been stripped away by a process called RAM pressure stripping, where the galaxy plows through the dense intracluster medium and loses its own gas in the process. This stripping, combined with the galaxy's internal consumption of gas billions of years ago, left it barren of star-forming fuel. But perhaps the strongest evidence of all comes from its stellar ages. Detailed spectroscopic studies allow astronomers to read the ages of stars like rings on a tree. By comparing the absorption lines of various elements in a galaxy's spectrum to stellar population models, researchers can reconstruct its star formation history. In the case of NGC 1277, these studies reveal that more than 90% of its stars were formed within the first 3 billion years of the universe. After that, star formation plummeted to essentially zero. For the last 10 billion years, the galaxy has been silent, a stellar graveyard with no signs of renewal. This shutdown appears to have been sudden. Unlike galaxies that taper off in their star formation gradually, NGC 1277 seems to have experienced a rapid quenching event. Its starburst phase was intense, producing a dense population of stars in a short time, but then it stopped abruptly. Astronomers theorize that feedback from its monster black hole may have played a role. As the black hole accreted matter, it could have unleashed powerful outflows of energy that heated or expelled the galaxy's gas, preventing further star formation. Whatever the mechanism, the result was permanent dormancy. The supermassive black hole at its core. There is a center engine in every galaxy, but NGC 1277's engine is a lot bigger than its host. There is one of the strangest black holes ever found right in the middle of this small object. It's not just big compared to other stars, it's monster-sized, with billions of times the mass of our Sun. Astronomers see this one object as the most important part of NGC 1277. This is why it has become one of the most studied galaxies in the last 10 years. Black holes are regions where gravity has collapsed matter so intensely that not even light can escape. At the centers of galaxies, supermassive black holes, millions to billions of solar masses, are the norm. The Milky Way, for example, hosts Sagittarius A star, weighing in at about 4 million suns. NGC 1277's black hole dwarfs that, with early measurements suggesting an astonishing 17 billion solar masses. Later refinements reduced that estimate slightly, but even at the lower end, closer to 12 billion, it remains one of the most massive black holes ever confirmed. To understand just how extreme this is, consider the usual ratio between a galaxy's stellar mass and its black hole. In most galaxies, the central black hole accounts for about 0.1% of the total mass of the stars. In NGC 1277, the black hole makes up between 10% and 14% of the galaxy's stellar mass. That's 100 times larger than expected. It would be like finding that your car's engine weighs almost as much as the entire car. Such an imbalance is not only rare, it challenges our entire understanding of how galaxies and black holes grow together. Careful study of how stars move led to the finding of this monster. Integral field spectroscopy was used to find out how fast the stars in the middle parts of NGC 1277 were moving. The stars were moving at very high speeds, much faster than they should have if the galaxy's visible stars and dark matter were the only things pulling them together. The easiest answer is that there is a huge black hole in the middle that bends space-time and controls the paths of everything in its path. What's even more amazing about this black hole is how far its effects reach. Most of the time, a giant black hole's gravitational field is not very big compared to the galaxy as a whole. In NGC 1277, on the other hand, the black hole controls a much bigger part of the galaxy's center. Part of the reason for this is that the galaxy is so small that there isn't much mass on the edges to fight the black hole's pull. As a result, the galaxy's center black hole not only holds it together, but also runs it. Scholars sometimes say that NGC 1277 is a galaxy dominated by a black hole. This saying gets to the heart of what makes it special. In galaxies, the center black hole is just one of many important parts. But here, it is the most important part. The stars, the gas or lack of gas, and the structure as a whole all circle around this central monster, both physically and metaphorically. NGC 1277 is more like a black hole wrapped around a galaxy than a galaxy with a black hole inside it. How could such an enormous black hole form in such a relatively small galaxy? That's the puzzle that makes NGC 1277 so important. One possibility is that the black hole grew extremely rapidly in the early universe, perhaps feeding on vast amounts of gas during a short-lived starburst phase. Another theory suggests that it may have started from an unusually massive seed black hole, far larger than the normal seeds thought to form from the first stars. Whatever the mechanism, it must have occurred quickly, because the galaxy shows no evidence of continued growth after its initial burst of activity. The presence of such a massive black hole also has implications for the galaxy's long dormancy. Black holes that accrete matter release enormous amounts of energy in the form of radiation and jets. This feedback can heat or expel gas from the galaxy, shutting down further star formation. Astronomers suspect that NGC 1277's central black hole may have quenched its galaxy early, blasting away the raw material needed to make new stars and locking the system into its fossil-like state. In that sense, the black hole is not only the ruler of NGC 1277, it is the architect of its relic status. Even though it's very big, this black hole is strangely quiet today. Unlike the glowing quasars of the early universe, NGC 1277 doesn't seem to be accreting anything at the moment. There are no bright jets, strong X-ray emissions, or other clear signs that they are eating a lot. It looks like it's not doing anything and is happy to sit on its throne of stars and watch over a galaxy that has stopped changing for a long time. Black hole mass compared to galaxy size. When physicists first told the world about NGC 1277's black hole, it wasn't just the number of billions of solar masses that shocked them. It was also how wildly out of proportion that number was compared to the rest of the galaxy. A galaxy's relationship with its center black hole usually follows a pretty tight pattern. Black holes are big in galaxies and small in galaxies. But NGC 1277 breaks that rule so badly that it almost looks like a mistake in the universe's printing. We need to compare the black hole's mass to the size of the galaxy that it is inside to get a sense of how big this strange thing is. In the Milky Way, Sagittarius A star weighs about 4 million solar masses, while the stellar mass of the galaxy is several hundred billion solar masses. That means our black hole makes up only about 0.01% of the total. This is typical across the universe. Central black holes are massive, but compared to the hundreds of billions of stars around them, they remain relatively modest. Now look at NGC 1277. Early estimates placed its central black hole at 17 billion solar masses, later revised to around 12 billion. Even using the lower figure, the black hole makes up a staggering 10–14% of the galaxy's total stellar mass. That's more than 100 times the usual ratio. In other words, NGC 1277 is less a galaxy with a black hole than a black hole with a galaxy attached to it. Its central monster is proportionally so dominant that it dwarfs not just Sagittarius A star, but even the black holes in the largest galaxies of the known universe. This ratio is what makes NGC 1277 such a challenge for astrophysics. The established relationship between black hole mass and galaxy mass, often referred to as the M-sigma relation, has been a cornerstone of galaxy evolution theory. It suggests that galaxies and their black holes grow together, linked by feedback processes that regulate their relative sizes. NGC 1277 smashes through that framework. Its black hole is too big for its galaxy, suggesting that at some point in the early universe, the black hole ran ahead of its host and never looked back. The size of the host galaxy only adds to the puzzle. NGC 1277 spans about 10,000 light-years across, a tenth the diameter of the Milky Way. Yet its central black hole outweighs our own by a factor of thousands. Imagine a town of 10,000 people whose mayor weighs more than everyone else combined. That's the kind of imbalance we're talking about. This extreme disproportionality has led astronomers to describe NGC 1277 as a black hole-dominated galaxy. How could such an oversized black hole exist in such a small galaxy? There are several competing theories. One is that NGC 1277 formed its black hole very early, during the first billion years of cosmic history, when conditions favored rapid growth. Massive seed black holes may have formed from the direct collapse of primordial gas clouds, bypassing the smaller stages that led to ordinary black holes. If NGC 1277 started with such a massive seed, its black hole could have ballooned quickly, while the galaxy around it stalled in growth. It's also possible that NGC 1277 was once a part of a much bigger galaxy. But over billions of years, it was broken up by interactions with other galaxies in the Perseus Cluster. It's possible that what we see now is the thick core of a galaxy that used to be very big, with a black hole that is way too big for its surroundings. However, this idea has problems, because all of the stars in NGC 1277 are the same age, and there are no signs of the starbursts caused by mergers that we'd expect if it had been stripped. In general, the data points to the fact that it has always been compact, not lessened. The extreme ratio also invites comparisons with other galaxies. Even the largest known galaxies, like IC 1101, which spans millions of light-years, don't have black holes that take up such a huge fraction of their stellar mass. Their central black holes weigh tens of billions of solar masses, but their host galaxies are so enormous that the ratio remains balanced. NGC 1277, by contrast, is tiny and dense, amplifying the dominance of its black hole. It's like finding an elephant crammed into a doghouse. The scale simply doesn't add up. This mismatch also changes how the galaxy works on the inside. More than half of the center part of NGC 1277 is affected by the black hole's gravitational pull. Stars that are orbiting within thousands of light years of it feel its pull directly and move at speeds that could only be caused by such a huge center. This is because the galaxy is very small, so the black hole controls almost everything inside it. In real life, you can't understand the world without looking at its black hole as the most important part. The ratio of black hole to stellar mass. Ratios are useful for researchers because they give them a sense of what's going on. Like the mass of a black hole, a single number is amazing, but it only means something when compared to something else. The most important thing to compare in galaxies is the mass of the black hole in the middle and the mass of the stars that make up the galaxy. This ratio is so constant across the universe that it is now one of the most important ideas in science. But NGC 1277 doesn't just break this rule, it completely breaks it. It has the highest ratio of black holes to stars' mass that has ever been proven. In the typical galaxy, the central black hole is a small but vital part of the system. For spiral galaxies like the Milky Way, the black hole makes up about 0.01% of the galaxy's stellar mass. For larger elliptical galaxies, the ratio might creep up to 0.1%. This correlation has been so reliable that it gave rise to the so-called M-sigma relation, which links the velocity dispersion of stars in a galaxy to the mass of its central black hole. The idea is that galaxies and their black holes co-evolve. As the galaxy grows, the black hole grows in step, maintaining a predictable balance. Now consider NGC 1277. Its stellar mass is estimated at around 1.2 trillion solar masses, while its black hole has been measured between 12 and 17 billion solar masses, depending on the study. Divide one by the other, and you get a ratio of around 10–14%. That is 1 to 2 orders of magnitude higher than the universal norm. Instead of a black hole being a tiny fraction of the galaxy, in NGC 1277, the black hole takes up a huge slice of the total mass. It is like finding out that the engine of your car accounts for nearly a third of the vehicle's total weight. This ratio is so unusual that it has led some astronomers to question whether the measurements are correct. After all, if every other galaxy in the universe follows one pattern, why should NGC 1277 be different? Some later studies, using alternative methods, suggested that the black hole might be somewhat smaller, perhaps closer to 5 billion solar masses. Even in that case, though, the ratio remains far above the norm. Whether the number is 5 billion or 17 billion, the point stands. NGC 1277 is an outlier of staggering proportions. There is a very important thing we can learn from the ratio about how galaxies change over time. It's possible for the black hole to grow faster than the world. When it gets big enough, its feedback loops of jets, winds, and radiation can heat or push out the gas that would normally power new stars. In the meantime, the black hole is still too big compared to the mass of the stars, so the galaxy can't grow any bigger. It looks like that's exactly what happened in NGC 1277. In the early universe, its black hole ate up gas and energy so quickly that it starved its host galaxy. This stopped the stars from moving and stopped evolution from happening. The ratio also highlights why NGC 1277 is such a key target for testing galaxy formation models. If galaxies like this exist, then the rules of coevolution aren't as universal as once thought. There must be pathways where black holes grow disproportionately fast, leaving their hosts permanently stunted. This has forced theorists to refine their models, allowing for scenarios where extreme ratios emerge under certain early universe conditions. The stellar to black hole ratio also has consequences for the dynamics of the galaxy. In most galaxies, the gravitational potential is dominated by the stars and dark matter, with the black hole only ruling the innermost region. In NGC 1277, the black hole's dominance extends much further out. It influences not just the core, but much of the galaxy's inner structure. Stars orbit under its overwhelming pull, creating velocity dispersions that betray its hidden presence. The ratio, in this sense, isn't just a number, it's written directly into the motions of every star in the galaxy. Putting NGC 1277 next to other galaxies shows how far out there it really is. Even the biggest galaxies in a cluster, like the millions of light-year-wide giant ellipticals, have black holes that make up less than 1% of their star mass. Even though NGC 1277 is smaller than many of those giants, its black hole weighs 10 to 100 times more than any of them. Techniques used to measure its black hole. Experts try to figure out how to measure something that is 220 million light-years away and doesn't give off any light of its own. Black holes can't be seen directly, but the way they change the movements of stars and dust around them lets us know they are there and how big they are. In the case of NGC 1277, scientists had to use the most advanced observing tools to figure out how heavy the monster in the middle of the galaxy was. Spectroscopy, high-resolution images, and complex models were all used together in this process. All of these methods work together to show a black hole that is so big it doesn't follow the normal rules of physics. The first method used to detect NGC 1277's black hole was stellar dynamics. By observing the velocities of stars orbiting close to the galaxy's center, astronomers can infer the gravitational pull holding them in place. The faster the stars move, the more mass must be hidden at the core. In NGC 1277, stars were racing around at such extreme speeds, hundreds of kilometers per second, that the only explanation was a central black hole weighing billions of solar masses. To gather this data, astronomers relied on spectroscopy, particularly integral field spectroscopy, IFS. This technique allows them to capture not just the light from one point, but the spectrum of light across a two-dimensional field. By spreading starlight into its component wavelengths, they can measure Doppler shifts, the subtle stretching or compressing of light caused by motion. In practice, this means they can map how stars move toward or away from us in different parts of the galaxy, creating a velocity map. For NGC 1277, those maps revealed steep velocity gradients near the center, a telltale sign of an overmassive black hole. The Hubble telescope in Texas, which has a strong spectrograph that can measure the motions of stars very accurately, was one of the major tools used. More observations were made by the Keck Observatory in Hawaii and the William Herschel telescope in Spain. Adaptive optics were used to make the view clearer. Adaptive optics is very important for this kind of work because it fixes the fuzz that Earth's atmosphere causes, making pictures that are almost as clear as those taken from space. Because of this, scientists were able to get closer to the center of the galaxy, where the black hole has the most power. Space-based observations from the Hubble Space Telescope provided another layer of evidence. Hubble's sharp imaging resolved the compact structure of NGC 1277 and confirmed that its stars were concentrated into a dense central bulge. By combining Hubble's photometric data with ground-based kinematic data, astronomers could build detailed models of the galaxy's mass distribution. These models consistently required a massive black hole to explain the observed stellar motions. Jeans modeling was another useful way. It is a mathematical approach that uses the equations of stellar dynamics to connect the observed differences in star speeds to the underlying mass distribution. By using models to fit the data, scientists could test different ideas, like a black hole that is smaller or one that has more dark matter gathered in its core. The best fits consistently needed a black hole that was much bigger than anyone had anticipated. Astronomers are also investigating the chance of using gas kinematics, which involves following the movements of interstellar gas close to a black hole to determine its mass. However, NGC 1277 doesn't have much cold gas, which makes this method less useful. Instead, the attention stayed on the stars. whose paths are directly affected by the black hole's pull. The robustness of these measurements is part of what makes NGC 1277 so compelling. Independent teams using different instruments and methods have arrived at similar conclusions. The black hole is enormous, far beyond what its galaxy should host. Even though later studies revised the initial estimate of 17 billion solar masses down to closer to 12 billion, the essential story remains unchanged. The black hole is still proportionally the most extreme ever measured. There is always some risk when estimating black holes from such a far away. Some experts have said that the models might overestimate the role of the black hole by underestimating the role of dark matter or the galaxy's stars. Some people think that better tools, like the James Webb Space Telescope, JWST, or the soon-to-be-built Extremely Large Telescope, ELT, could make the numbers even more accurate. But no matter what the exact number is, everyone agrees that NGC 1277's black hole is one of the biggest known and clearly rules its galaxy. Hubble observations of NGC 1277. The Hubble Space Telescope is one of the first tools scientists use to get a better look at galaxies far away. Hubble has taken clear, high-resolution pictures that have changed almost every area of science since it was launched in 1990. Hubble played a key part in NGC 1277. Astronomers would never have been able to confirm how strange this system really is without being able to look deep into the galaxy's dense heart. NGC 1277 sits about 220 million light-years away, which is close by cosmic standards but still far enough that details blur when viewed from ground-based observatories. Even with adaptive optics, resolving the innermost regions is challenging. Hubble bypasses this limitation because it orbits above Earth's atmosphere. Its sharp images revealed NGC 1277's true shape, a compact elliptical galaxy with a dense smooth bulge and little evidence of recent mergers or star-forming regions. This first impression already hinted at its relic nature. But Hubble's contribution went far beyond pretty pictures. By pairing its imaging data with spectroscopic measurements from other telescopes, astronomers could build precise models of the galaxy's mass distribution. Hubble's images traced the light profile of NGC 1277, the way brightness falls off as you move outward from the center. This brightness distribution, when compared to the stellar velocity dispersions measured from the ground, allowed scientists to test whether a massive black hole was truly needed to explain the observations. The answer was yes. In 2012, the original study led by Remco van den Bosch used Hubble's data as part of the evidence for a black hole of about 17 billion solar masses. The sharpness of Hubble's wide-field camera helped lock down the compactness of the galaxy's central bulge, which was critical for the dynamical models. If the stars were spread out over a larger radius, their velocities could have been explained without such a massive black hole. But Hubble showed they were packed tightly, leaving no other option but an overmassive central engine. Hubble also revealed what NGC 1277 lacked. Its images showed no spiral arms, no star-forming knots, and no obvious tidal tails from mergers. It was a smooth, featureless oval, a galaxy that had not changed much in billions of years. In the Perseus Cluster, where interactions and distortions are common, this simplicity stood out. The absence of fine structure reinforced the idea that NGC 1277 is a relic galaxy, a frozen fossil from the early universe. The proof of its small size was another important fact. The outer diameter of NGC 1277 was found by Hubble to be just over 1,000 parsecs, which is equal to 3,200 light-years. Compared to typical ellipticals, which can be tens of thousands of light-years across, that is a tiny comparison. This tightness not only explained why the black hole's pull went so far, but it also put NGC 1277 in line with red nugget galaxies that can be seen at very high redshift. It was as if one of those old nuggets had been moved into our garden in space so Hubble could study it in greater detail. After that, Hubble views made the picture even clearer. The black hole's mass was lowered to about 12 billion solar masses in a new study released in 2018. The study used updated modeling methods and more Hubble data. Even though this number was lower than the original 17 billion, it still made it one of the most massive black holes ever found, and its ratio to the galaxy's star mass stayed very high. The revision showed how important it is to keep looking at data again using better methods, but it didn't change the fact that NGC 1277 is an oddball. The things Hubble saw also helped put NGC 1277 in relation to its neighbors. Astronomers proved that it was truly unique by matching its light profile to that of other galaxies in the Perseus Cluster. Most of the galaxies in the cluster had long halos or other signs of interacting, but NGC 1277 looked like it was completely clean. Crisp pictures from Hubble caught this difference very clearly, showing how strange it was to find such a well-preserved fossil in a busy cluster setting. Kinematics of stars orbiting the core. Even though galaxies look still in pictures taken by telescopes, they are not at all still inside. As a result of the gravity of everything around them, stars are always moving around. Astronomers study these movements, which they call kinematics, to find secrets that are deep inside the universe. For NGC 1277, the movement of its stars proved beyond a doubt that it had a monster black hole. Their incredible speeds made it clear that something incredibly huge is at the center. The first clue came from measuring stellar velocity dispersion, the range of speeds at which stars move in different directions. In a typical compact elliptical galaxy, stars near the center move a few hundred kilometers per second, with the velocities gradually tapering off farther out. In NGC 1277, the story was different. Stars near its core were whipping around at speeds exceeding 400 kilometers per second, some even approaching 500. For comparison, stars in the Milky Way's bulge usually move closer to 100 kilometers per second. The blistering pace inside NGC 1277 was a red flag. Only a central black hole of extraordinary mass could drive stars to such velocities. To measure these speeds, astronomers used integral field spectroscopy, which captures not just the spectrum of light at one point, but across a two-dimensional patch of the galaxy. By analyzing the Doppler shift of absorption lines in starlight, they could determine whether stars in different regions were moving toward us or away from us, and at what speed. The resulting velocity maps showed dramatic gradients near the core, with stars orbiting faster and faster the closer they were to the center. This steep rise is exactly what you'd expect if a supermassive black hole were anchoring the galaxy. The stellar kinematics also showed that stars move in different ways, such as in ordered rotations or more random circles backed by pressure. The stars in NGC 1277 are not neatly arranged in a disk that spins. Instead, they move in a random way, with random speeds being the most common. These kinds of things usually happen in irregular galaxies, which don't grow through slow, steady disk accretion, but in NGC 1277, the black hole makes this effect stronger, making a velocity field that is more extreme than in almost any other galaxy of the same size. What makes the case even more convincing is the sphere of influence of the black hole. Normally, the gravitational dominance of a black hole extends only a small fraction of a galaxy's radius, often less than 1% of the total. In NGC 1277, because the galaxy is so compact and the black hole so large, the sphere of influence covers a substantial fraction of the core. This means that the black hole's gravity is not just a local feature, it dictates the motions of stars across much of the central region. The stars themselves become tracers, their high speeds a silent testimony to the mass hidden in the center. A noteworthy finding from these motion studies was that the stars in NGC 1277 are moving too fast for the galaxy's stellar mass to explain. When you plug in the total mass of its stars and dark matter and run the math, the speeds that are expected are very different from what is seen. The math only makes sense when a black hole with billions of solar masses is added to the model. This was the most important piece of proof that proved the black hole was one of the biggest ever recorded. These stellar motions also explain why the galaxy appears so smooth and compact. In galaxies with significant rotation, such as spirals, the stars organize into disks and arms. But in NGC 1277, the random high-speed orbits create a spheroidal shape, with no internal structure beyond the central bulge. It is a galaxy sculpted by speed, its stars locked in a gravitational ballet dictated by a single, overwhelming partner. The motion data made me think of a puzzle. The stars don't seem to interact with new gas or younger stellar groups very much. Usually this much gravity confusion would lead to instability or starbursts. But in NGC 1277, the old stars just move around quietly, not being touched by the new growth. This supports the idea that the galaxy has been sealed off from the rest of the universe for a very long time. Why its black hole is considered overmassive. Astronomers use the word overmassive to describe black holes that are bigger than what scientists have seen for decades. It doesn't just mean big. Many galaxies are home to black holes that are so big they weigh billions of suns. The black hole is overmassive if it is much bigger than it should be for the size of the galaxy it is engulfing. The center giant in NGC 1277 is the very meaning of an overmassive black hole. It is one of the most extreme examples of this type of object ever seen. To appreciate just how unusual this is, we need to look at the rules that black holes normally follow. Astronomers have long known that the mass of a galaxy's central black hole correlates with properties of the host galaxy, like the total stellar mass or the velocity dispersion of stars in the bulge. This relationship is known as the M-sigma relation, and it has been a cornerstone of galaxy evolution theory. According to this model, galaxies and their black holes grow together in a kind of cosmic partnership. As galaxies merge and form new stars, their black holes feed and expand, keeping a fairly consistent ratio. The term overmassive here isn't just academic. It represents a serious challenge to how we think galaxies evolve. If the coevolution model is correct, then galaxies and black holes should track each other's growth closely. Yet NGC 1277 suggests that under certain conditions, black holes can grow unchecked, leaving their hosts permanently stunted. The implication is that the cosmic partnership isn't as universal as once thought. Sometimes the black hole dominates, shaping the destiny of the entire system. Comparing NGC 1277's black hole to others in galaxies the same size is another way to understand why it is so huge. In ellipticals that are close together and have about the same stellar mass, the center black holes are usually between a few 100 million and 2 billion solar masses heavy. That's still very big, but it's in the normal range. On the high end of this range, NGC 1277's black hole is 5 to 10 times bigger. When you walk into a small town, you find a tower that is as tall as the largest buildings on Earth. It doesn't fit in at all with the rest of the town. This overmassive status also raises questions about how the black hole reached such a size in the first place. Did it form from a massive seed, hundreds of thousands of suns heavy, that collapsed directly from a primordial gas cloud? Did it gorge on gas in the early universe, at rates far exceeding the usual Eddington limit, the theoretical cap on how fast black holes can grow? Or did it experience early mergers with other supermassive black holes before its galaxy's growth stalled? Each possibility is extreme, but so is the black hole it tries to explain. The galaxy is a relic, which is directly linked to the term overmassive. One popular idea says that the black hole grew very quickly at the beginning, putting out enough energy to stop the galaxy from making new stars. Radiation and jets could have shot away the gas that new stars need, keeping the galaxy in a state similar to that of a fossil. In this way, the black hole wasn't overmassive by chance. It made the conditions that stopped NGC 1277 in its tracks. The galaxy we see now may be a direct effect of how the black hole ruled in the past. Critics have pointed out that some of the black hole mass estimates might be inflated. A 2018 study using updated dynamical models suggested a smaller value of around 12 billion solar masses rather than 17 billion. But even at this lower estimate, the black hole remains vastly oversized compared to the galaxy. The label overmassive still applies, because the black hole's share of the total stellar mass is still more than 100 times what the M-sigma relation predicts. Whether it's 12 billion or 17 billion, the anomaly is undeniable. Comparison with the Milky Way's black hole. To truly grasp how extraordinary NGC 1277's black hole is, it helps to hold it side by side with one we know more intimately, our own. At the heart of the Milky Way lies Sagittarius A star, the supermassive black hole we've spent decades observing in exquisite detail. It is massive by human standards, weighing in at about 4 million times the mass of the Sun. But when set against the Titan inside NGC 1277, Sagittarius A star looks almost delicate. This contrast highlights not just the size difference, but also the radically different evolutionary stories of the two galaxies. The Milky Way is a sprawling spiral galaxy roughly 100,000 light-years across, containing between 200 and 400 billion stars. Its black hole accounts for just 0.01% of the galaxy's stellar mass, a ratio well in line with the standard M-sigma relation. Sagittarius A star is large enough to hold the galaxy together at the center, but not so large that it dominates the system. In fact, much of the Milky Way's structure, its spiral arms, its halo of stars, and its streams of gas, owes little to the black hole's direct influence. Our galaxy is a balanced ecosystem with the black hole one component among many. Now compare this to NGC 1277. Its black hole is estimated at 1217 billion solar masses, roughly 3,000 to 4,000 times larger than Sagittarius A star. And yet NGC 1277 itself is only about 10,000 light-years across, 1/10 the size of the Milky Way, with around 1 trillion stars packed into its compact body. The ratio of black hole to stellar mass is closer to 14%, hundreds of times greater than the Milky Way's. Put simply, NGC 1277's black hole is not just larger, it is wildly oversized compared to its host, whereas the Milky Way's fits neatly within expectations. Another striking difference lies in activity. Sagittarius A star is relatively quiet today. It occasionally flares as gas clouds pass near its event horizon, but for the most part it is a dormant black hole. Astronomers can study it by tracking the orbits of nearby stars, which move at blistering speeds but remain visible in infrared light. By contrast, NGC 1277's black hole appears to have burned bright and fast in the early universe, consuming gas so rapidly that it shut down star formation in its galaxy. Today, it too is silent, but its silence comes after an era of explosive growth that froze its host into a relic. The Milky Way never experienced such an extreme quenching event. The environments around the two black holes also differ dramatically. Sagittarius A star sits in a disk galaxy rich with gas, dust, and ongoing star formation. Stars continue to form in the spiral arms, fueled by cold molecular clouds. The galaxy evolves dynamically, with interactions, accretion, and gradual growth shaping its structure. NGC 1277, on the other hand, is barren. Its black hole expelled or consumed the gas billions of years ago, leaving behind a sterile fossil with no capacity to grow. This makes NGC 1277 less like a living galaxy and more like a preserved relic of cosmic history. From a theoretical standpoint, comparing these two galaxies underscores the diversity of black hole-galaxy relationships. The Milky Way is a poster child for the co-evolution model. The galaxy and its black hole grew in harmony, maintaining a predictable balance. NGC 1277 is the outlier, showing what happens when that balance breaks. It suggests that black holes can sometimes grow far faster than their galaxies, decoupling from the expected pattern and reshaping their hosts in the process. There's also a lesson in gravitational influence. The gravitational pull of Sagittarius A star extends only a few light-years, influencing the orbits of stars in its immediate neighborhood, but not dominating the larger galaxy. In NGC 1277, the black hole's sphere of influence stretches across a much larger fraction of the galaxy. Its gravity dictates the motions of stars across thousands of light-years, turning the entire galaxy into a kind of extended black hole environment. This is why astronomers sometimes describe NGC 1277 as a black hole wrapped in a galaxy, rather than a galaxy with a black hole. Comparisons like these help place our galaxy in perspective. The Milky Way may feel enormous to us, but on the cosmic stage, it is a middleweight. NGC 1277, by contrast, is a heavyweight in disguise, a small galaxy whose central black hole is among the most massive known. If Sagittarius A star were suddenly replaced by NGC 1277's monster, the Milky Way would be torn apart. Star orbits would destabilize, the galactic structure would collapse, and the spiral arms would not survive the gravitational chaos. Our very existence depends on the fact that our galaxy's black hole is modest, not monstrous. Astronomers see this comparison as a reminder of cosmic variety. No single galaxy can tell the whole story. The Milky Way represents a path of steady, balanced growth, while NGC 1277 represents a path of extreme imbalance, locked into its relic state by an overmassive black hole. Together, they show that the universe writes many different scripts, some orderly, others chaotic. But NGC 1277 has earned a nickname that captures this imbalance perfectly: the galaxy that shouldn't exist. Next, we'll uncover where that nickname came from and why it stuck in the astronomical imagination. Nickname: the galaxy that shouldn't exist. Science is usually cautious with words, but every now and then, a discovery shakes researchers enough that dramatic nicknames slip through. NGC 1277 is one such case. When astronomers realized just how oversized its central black hole was compared to the rest of the galaxy, headlines around the world quickly branded it the galaxy that shouldn't exist. This nickname captured the shock and disbelief that rippled through the astronomical community when the discovery was first announced. The phrase has its roots in the original 2012 study led by Remco van den Bosch. His team, analyzing stellar velocity data, concluded that NGC 1277 harbored a black hole weighing as much as 17 billion suns. To put that in context, such a mass is typically reserved for the central black holes of enormous galaxy clusters, not for a compact system only 1/10 the size of the Milky Way. It was like finding a skyscraper in the middle of a tiny village. The mismatch seemed so extreme that many wondered whether the galaxy could even exist under such conditions, hence the nickname. The nickname resonated because it highlighted the galaxy's defiance of the rules. According to accepted theory, galaxies and their black holes grow together, maintaining a predictable relationship between their sizes. NGC 1277 violated this relationship by an order of magnitude. The black hole accounted for about 10–14% of the galaxy's stellar mass, compared to the standard 0.1%. This wasn't just an exception to the rule, it was a galaxy rewriting the rulebook altogether. Media coverage amplified the phrase. Science outlets like Nature News, National Geographic, and Space.com seized on the catchy tagline to explain the discovery to the public. The galaxy that shouldn't exist quickly became shorthand for the puzzle of NGC 1277. It conveyed both the drama of the finding and the idea that this system was fundamentally at odds with what astronomers thought they knew. Within months, the nickname stuck, and even professional astronomers began using it informally in talks and papers. The name also reflects the galaxy's paradoxical survival. NGC 1277 is located in the Perseus Cluster, a dense environment where galaxies are constantly colliding, merging, or being stripped of material. In such a chaotic neighborhood, small galaxies rarely remain unchanged. Yet NGC 1277 has persisted as a compact fossilized relic, untouched for over 10 billion years. Its survival in this environment is nearly as baffling as the size of its black hole. From that perspective, it truly feels like a galaxy that has no right to still be here. What gives the nickname extra weight is how it ties into larger cosmic questions. If NGC 1277 exists, then the processes that govern galaxy evolution are not as uniform as once believed. It suggests that there are rare pathways where black holes run ahead of their hosts, consuming gas and shutting down growth. These pathways produce galaxies that appear impossible under standard models, but which nevertheless exist as real fossils of the early universe. In that sense, calling NGC 1277 the galaxy that shouldn't exist is less about literal impossibility and more about scientific humility. It reminds us that nature often finds ways to surprise us. The nickname also fits because NGC 1277 seems to break multiple expectations at once. Its compact size is unusual for a galaxy that old. It should have puffed up through mergers. Its stellar population is uniformly ancient, with no signs of rejuvenation. Its lack of cold gas makes it sterile, yet it sits in a cluster where interactions could have easily delivered fresh fuel. And of course, its black hole is monstrously out of proportion. Each of these quirks might be explainable on its own, but together they add up to a galaxy that feels fundamentally out of step with the cosmic order. Over time, the phrase "the galaxy that shouldn't exist" has become a rallying point for studies of relic galaxies. Astronomers now know of a handful of other compact systems with oversized black holes, like MRK 1216 and NGC 1271. These discoveries suggest that NGC 1277 is not entirely unique, but rather part of a rare class of galaxies that froze in time. Still, NGC 1277 remains the poster child, the one that first forced the issue into the spotlight. It is the galaxy most strongly associated with the idea that cosmic evolution has exceptions. Some scientists prefer more technical labels like relic galaxy or black hole-dominated galaxy. But even in research circles, the dramatic nickname persists. It conveys the sense of wonder and disbelief that still surrounds this object. After all, science advances not just through equations, but through moments of astonishment, moments when we realize the universe has written a script we didn't expect. But NGC 1277's nickname is only the beginning of its mystery. Beyond being a galaxy that shouldn't exist, it forces us to ask deeper questions. How did its black hole grow so enormous, so quickly in the early universe? And why did the galaxy itself stop evolving? Theories on how the black hole grew so large. If NGC 1277's black hole is the tyrant at the heart of a fossil galaxy, then the natural question is, how did it get so massive in the first place? Astronomers have spent more than a decade wrestling with this mystery. The black hole isn't just large, it is disproportionately huge, far bigger than any galaxy of its size should host. To explain this, scientists have proposed several theories, ranging from early universe feeding frenzies to the possibility of exotic black hole seeds that defy standard models. One leading theory is rapid early growth through gas accretion. In the first billion years after the Big Bang, the universe was a much denser place. Galaxies were smaller, closer together, and filled with vast reservoirs of cold gas. Under these conditions, black holes could feed at extraordinary rates. If NGC 1277's central seed black hole began consuming gas in a runaway fashion during this period, it could have reached billions of solar masses before the galaxy itself had time to grow much larger. Essentially, the black hole sprinted ahead while the galaxy stalled. This idea is supported by the high metallicity of NGC 1277 stars. They appear to have formed in a short, intense burst of activity early on. Such a starburst would have funneled gas inward, feeding both star formation and black hole growth simultaneously. But once the black hole reached a critical size, its feedback, jets, winds, and radiation could have blasted out the remaining gas. This feedback loop would quench further star formation, locking the galaxy into its compact relic state. In this scenario, the black hole's rapid growth isn't just an accident, it's the very reason the galaxy looks the way it does today. Another possibility is that NGC 1277 started with an unusually massive black hole seed. Normally, black holes are thought to form from the collapse of massive stars, giving birth to light seeds of a few tens to hundreds of solar masses. Over time, these can grow into supermassive black holes. But there may also be heavy seeds, forming directly from the collapse of giant primordial gas clouds in the early universe. These could weigh tens of thousands or even a million solar masses right from the start. If NGC 1277 formed with one of these heavy seeds, its black hole would have had a huge head start, explaining its dominance today. A third theory considers black hole mergers. In the crowded environment of the early Perseus Cluster, galaxies often collided and merged, and their central black holes would have merged as well. NGC 1277 might have swallowed several smaller galaxies in quick succession, each time adding their central black holes to its own. This process could have boosted its black hole to billions of solar masses very quickly. However, this explanation runs into problems, because the galaxy's stars are uniformly old, with no signs of the mixed populations you'd expect from multiple mergers. It seems unlikely that NGC 1277 experienced enough mergers to explain its monster black hole. Another idea ties into dark matter. Some models suggest that NGC 1277 might have formed in a region of unusually dense dark matter, providing extra gravitational potential to funnel gas inward and accelerate black hole growth. However, recent studies indicate that NGC 1277 is surprisingly poor in dark matter compared to expectations, making this explanation less convincing. Still, the role of dark matter in shaping the growth of galaxies and black holes remains an open question. Whichever path the black hole took, one thing is clear: it grew very quickly, very early, and then stopped. The lack of cold gas in NGC 1277 today means it hasn't grown much in the last 10 billion years. This frozen growth pattern is unusual. Most supermassive black holes continue to accrete material over cosmic time, albeit at slower rates. NGC 1277's black hole appears to have reached maturity almost overnight, cosmically speaking, and then gone dormant. This rapid growth is why NGC 1277 is sometimes described as a fossil quasar. In the early universe, quasars were powered by black holes consuming enormous amounts of gas, shining brighter than entire galaxies. NGC 1277's black hole may have once been such a quasar, but after exhausting its fuel and shutting down its galaxy, it became silent. What we see today is the aftermath, a massive but quiet black hole sitting inside a galaxy that hasn't evolved since. These theories also carry broader implications. If NGC 1277's black hole grew so quickly, it suggests that other early black holes could have done the same. This might help explain how we already see quasars powered by billion solar mass black holes just a few 100 million years after the Big Bang. NGC 1277 could be the local nearby example of a process that was once common but is now rare. But, while we've explored how the black hole may have grown, another question lingers. Why didn't the rest of the galaxy keep up? Coming up, we'll examine the role that mergers, or the lack of them, played in shaping NGC 1277 into the relic it is today. Role of mergers, or lack thereof, in its evolution. Galaxies are social creatures. They rarely live their lives in isolation, and over billions of years they interact, collide, and merge with one another. These mergers are one of the main engines of galactic growth, building today's giant spirals and ellipticals out of smaller progenitors. For most galaxies, mergers are inevitable, especially in dense environments like the Perseus Cluster. But NGC 1277 seems to have bucked the trend. Its defining characteristic as a relic galaxy comes precisely from what didn't happen. It never went through the mergers that should have reshaped it. In the standard model of galaxy evolution, small galaxies formed early in the universe, then gradually combined into larger systems through repeated mergers. Each merger typically added new stars, stirred up gas, and often triggered bursts of star formation. Over time, this process puffed up the compact red nugget galaxies of the early universe into the large, extended ellipticals we see today. By this logic, NGC 1277 should have undergone several mergers over the past 10 billion years, growing larger and more diffuse. Yet, When astronomers study it, they find no evidence of such a history. The first clue comes from its uniformly old stars. If NGC 1277 had merged with other galaxies more recently, we would expect to see multiple generations of stars with different ages. Mergers tend to mix populations. Young blue stars from one galaxy get combined with older red stars from another. But spectroscopic analysis shows that NGC 1277 stars are almost all the same age, born in a single ancient burst more than 10 billion years ago. This suggests that no significant merger has occurred since that time. Another piece of evidence is the lack of structural scars. Galaxies that have experienced mergers often show tidal features, faint streams of stars pulled out during collisions, shells of material left over from disrupted companions, or warped shapes betraying gravitational encounters. High-resolution imaging of NGC 1277, especially with the Hubble Space Telescope, shows none of these features. Its light profile is smooth and symmetrical, more like an untouched fossil than a galaxy reshaped by violence. The environment of the Perseus Cluster makes this even more puzzling. Clusters are notorious for interactions. Galaxies in such dense environments are constantly passing close to one another, exchanging material, or even merging outright. That NGC 1277 has survived here without being disturbed suggests that it has been remarkably isolated, perhaps moving along an orbit that kept it out of the busiest regions of the cluster. While its neighbor NGC 1275 grew into a luminous giant through repeated mergers and accretion, NGC 1277 remained on the sidelines, a fossil in a field of activity. The absence of mergers may also help explain its overmassive black hole. Normally, mergers provide fresh gas to fuel both star formation and black hole growth, but they also add stellar mass, keeping the ratio of black hole to galaxy mass balanced. Without mergers, NGC 1277 missed out on this galaxy-wide growth. Its black hole had already ballooned during the early universe, but the host galaxy never caught up. This left the black hole dramatically oversized compared to its stellar population. In other words, the lack of mergers froze the galaxy while the black hole raced ahead. There is also the possibility that NGC 1277 did experience interactions, but of a very different kind, stripping rather than merging. In a dense cluster, smaller galaxies can be stripped of their gas and outer stars by the gravitational pull of larger neighbors, or by the hot intra-cluster medium. If NGC 1277 once had a more extended envelope, it might have been peeled away by such processes, leaving only its dense core. Some astronomers have suggested this as an explanation for its compactness. However, the uniform stellar ages argue against it. Stripping usually leaves signs of mixed populations, which are absent here. Another factor to consider is orbital dynamics within the cluster. NGC 1277 may have followed an orbital path that kept it out of the busiest merger zones near the cluster's center. If so, it could have avoided the kind of close encounters that would have disrupted its structure. Its survival would then be partly a matter of luck. An ancient galaxy that happened to drift into a safe orbit billions of years ago, preserving it as a relic. The lack of mergers also sheds light on NGC 1277's star formation history. In many galaxies, mergers bring in fresh gas, which collapses into new stars. Without mergers, NGC 1277 was cut off from these rejuvenating episodes. Once its initial starburst burned through its gas supply, no outside source replenished it. Combined with the feedback from its massive black hole, this ensured that star formation ended permanently. What was left was a galaxy that aged in place, unaltered for 10 billion years. In broader terms, NGC 1277 demonstrates that mergers are not inevitable for every galaxy. While the majority grow and change through collisions, a small handful escape that fate. These galaxies are the relics, time capsules that allow us to study what the universe looked like long ago. Without the absence of mergers, NGC 1277 would have become just another elliptical galaxy, indistinguishable from thousands of others. Instead, it remains unique. a fossil galaxy that forces us to rethink the diversity of galactic life histories. But while NGC 1277 avoided the usual growth and reshaping, it didn't escape evolution entirely. Its lack of change is itself a kind of evolution, a path of arrested development that froze it at an early stage. Why it's called a frozen-in-time galaxy? When astronomers call NGC 1277 a frozen-in-time galaxy, they're not being poetic. They mean it quite literally. This galaxy has barely changed in more than 10 billion years. While most galaxies evolved through mergers, starbursts, and gradual accretion of gas, NGC 1277 slammed on the brakes early and never restarted. It is a fossilized remnant of the early universe, preserved in nearly the same state as when it first formed. For scientists, it's like opening a time capsule buried since the dawn of galaxy formation. The story begins in the early universe, when gas clouds collapsed into compact, dense galaxies known as red nuggets. These galaxies were small by modern standards, only a few thousand light-years across, but incredibly dense, packed with stars formed in brief, furious bursts. Over the following billions of years, most red nuggets grew through mergers, gradually ballooning into today's giant ellipticals. But NGC 1277 did not. It looks today almost exactly like those red nuggets did billions of years ago. That's why astronomers describe it as frozen in time. One of the strongest indicators of its frozen status is the age of its stars. Spectroscopic studies show that nearly all of NGC 1277's stars formed in a single, short-lived burst more than 10 billion years ago. After that, star formation ceased. No new stars have been born since. Other galaxies typically show a mix of stellar ages, reflecting multiple episodes of star formation over cosmic history. NGC 1277 has no such variety. Its uniform stellar population is a frozen record of a single moment in the distant past. Another clue is its compact structure. Early galaxies were smaller and denser than today's ellipticals. Most expanded over time through mergers, puffing up into larger systems with extended halos. NGC 1277 never underwent this growth. Its radius is only about 10,000 light-years, tiny compared to most ellipticals of similar mass. Its shape and density are identical to the compact galaxies seen at high redshifts when the universe was less than a quarter of its current age. Observing NGC 1277 is like seeing one of those early galaxies frozen in the present day. The galaxy's lack of gas and dust reinforces this picture. Star formation requires cold gas as raw material. In most galaxies, mergers or accretion provide fresh supplies over time, but NGC 1277 has none. Observations in radio and millimeter wavelengths show it is almost completely devoid of molecular hydrogen, the fuel for new stars. Without this reservoir, its stellar population has been stuck in place for billions of years. Combined with the feedback from its overmassive black hole, which likely blew out or heated any remaining gas long ago, this left the galaxy sterile. Even its morphology supports the frozen label. Hubble images reveal a smooth, featureless oval with no spiral arms, no bar, no star-forming regions, and no tidal tails. It shows none of the scars or asymmetries typical of galaxies that have interacted with neighbors. Its surface brightness profile falls off steeply, exactly like the compact galaxies of the early universe. In short, everything about its structure screams ancient and unchanged. What's remarkable is not just that NGC 1277 is frozen, but that it survived this way inside the bustling Perseus Cluster. Clusters are violent environments where galaxies are constantly tugged by gravity, stripped by hot plasma, and even cannibalized by larger neighbors. That NGC 1277 avoided such fates for 10 billion years is astonishing. It suggests that its orbital path through the cluster kept it safe from major mergers, allowing it to remain a fossil amid chaos. It is a still frame in a movie that otherwise never stops running. The phrase, frozen in time, also reflects its scientific value. Because NGC 1277 hasn't evolved like other galaxies, it preserves the conditions of the early universe in its current form. By studying it, astronomers can reconstruct what galaxies were like during the first few billion years after the Big Bang, without having to look across billions of light years to faint, distant objects. In a sense, NGC 1277 is a cheat code for cosmology, letting us study early universe galaxies in our own cosmic backyard. It's also frozen in another sense, its black hole to galaxy ratio. While most galaxies saw their black holes and stellar masses grow in tandem, NGC 1277's black hole grew early and then stopped, leaving the ratio locked in place. The result is a permanent imbalance that has lasted for 10 billion years. The system is a snapshot of what happens when a black hole runs away with growth and then halts its host galaxy in its tracks. Of course, frozen doesn't mean completely static. Stars still orbit at high speeds, and some evolve into red giants, supernovae, and stellar remnants. But on the scale of galactic evolution, NGC 1277 hasn't changed in eons. It's like a glacier that still moves slowly, but looks unchanged to the naked eye. From a cosmic perspective, it is effectively frozen. But while NGC 1277's frozen state makes it a fossil, it also raises a question. How does its compact size tie into its black hole's dominance? How its compact size relates to black hole dominance. When astronomers describe NGC 1277 as compact, they mean it in the strictest sense. This galaxy is about 1/10 the diameter of the Milky Way, roughly 10,000 light-years across. Yet within that small footprint, it contains hundreds of billions of stars and a central black hole weighing billions of suns. The result is a system where density and gravity combine to give the black hole an oversized role, dominating the galaxy in ways that simply don't happen in larger systems. Its compactness is the key to why the black hole looms so large. The sphere of influence of a black hole, the region where its gravity overwhelms the pull of surrounding stars, depends on both the mass of the black hole and the density of the galaxy around it. In the Milky Way, Sagittarius A star has a sphere of influence spanning just a few light-years. The rest of the galaxy is too spread out for the black hole to control. But in NGC 1277, the stars are crammed much closer together, and the black hole is thousands of times more massive. This means its sphere of influence covers a huge fraction of the entire galaxy, pulling stars into orbits that respond directly to its gravity. In fact, velocity measurements show that the black hole's presence can be felt thousands of light-years from the center, well beyond the core, where we'd normally expect its control to fade. Stars in NGC 1277 whip around at 400–500 kilometers per second, speeds that can only be explained by the black hole's dominance. The compactness of the galaxy ensures that nearly everything is within the monster's gravitational reach. Where most galaxies have balance between black hole and stellar gravity, NGC 1277 is tilted sharply toward the black hole's rule. This compact structure is what links NGC 1277 to the class of early universe red nuggets. These dense galaxies were common around 10 billion years ago, but mostly vanished through mergers and growth. Their black holes would have played proportionally larger roles because the galaxies were so small. NGC 1277 survived as one of these nuggets, never growing larger, so its black hole's dominance never diminished. It is essentially an ancient red nugget, preserved into the modern era, still showing what happens when galaxies remain small and their black holes remain vast. The compact size also helps explain the black hole to stellar mass ratio. If NGC 1277 were a larger galaxy, even a monster black hole would be balanced by more stars and gas. But with such limited real estate, the black hole's share of the mass is dramatically inflated. That's why it accounts for 10–14% of the galaxy's stellar mass, hundreds of times the normal ratio. The compactness magnifies the imbalance, turning NGC 1277 into one of the most extreme outliers ever found. Another factor is the lack of an extended halo. Most galaxies, especially ellipticals, are surrounded by diffuse halos of stars and dark matter that dilute the gravitational influence of their central black holes. NGC 1277 has no such halo. It is all core, with no fluff. Without this extended mass to balance things out, the black hole's relative importance skyrockets. In essence, NGC 1277 is a bare-bones galaxy where the black hole is left exposed as the dominant player. Astronomers also point out that compactness is why the galaxy is so smooth and spheroidal. With stars packed tightly together, random motions dominate over ordered rotation. The black hole enhances this pressure-supported structure, keeping the galaxy shaped like a dense oval. In spirals, rotation prevents collapse and organizes matter into disks. But in a compact system like NGC 1277, random high-speed orbits create a gravitational pressure cooker, and the black hole acts as the lid holding it all together. The interplay between compactness and black hole dominance also explains why NGC 1277 is such a useful fossil for studying the early universe. High redshift surveys routinely find compact galaxies with oversized black holes, but they are so far away that they appear as faint smudges in telescope images. NGC 1277 gives astronomers a local laboratory to study the same conditions in far greater detail. Its compact structure has preserved the early relationship between galaxy and black hole in a way that larger, merger-driven galaxies cannot. Another angle is the role of feedback. In larger galaxies, star formation and gas accretion dilute the black hole's dominance. But in NGC 1277, the compactness and early quenching meant that feedback from the black hole had a greater relative effect. Once it blasted away the gas supply, the galaxy stopped evolving, freezing its small size permanently. The compact structure and overmassive black hole are therefore two sides of the same coin, each reinforcing the other. Compact galaxies also tend to be fragile, easily disrupted by mergers. That NGC 1277 has stayed compact for over 10 billion years suggests it avoided significant interactions. This too helped maintain the black hole's dominance. Had the galaxy merged and grown, the black hole's ratio would have dropped to normal levels. Its survival in this compact form is precisely what makes its imbalance so striking. In summary, NGC 1277's compact size is the amplifier that makes its black hole so dominant. By cramming hundreds of billions of stars into a small volume and pairing them with a monster black hole, the galaxy has created a system where gravity is unbalanced, velocity dispersions are extreme, and the central engine rules like nowhere else. It is a galaxy in miniature, but with a black hole fit for a giant. Coming up, we'll step back and look at NGC 1277's relationship with its neighbors in the Perseus Cluster, how such a fossilized relic managed to survive in a crowded cosmic city. Relationship with nearby galaxies in Perseus Cluster. NGC 1277 may be small and compact, but it doesn't live in isolation. It resides within the Perseus Cluster, one of the most massive and dynamic galaxy clusters in the nearby universe. This crowded environment, filled with thousands of galaxies and vast clouds of hot intracluster gas, is a place where encounters, stripping, and mergers are the norm. The fact that NGC 1277 has survived here for over 10 billion years in a nearly pristine state makes its relationship with its neighbors one of the most intriguing parts of its story. The Perseus Cluster is dominated by the giant galaxy NGC 1275, a central powerhouse with sprawling filaments of gas and one of the brightest X-ray outputs of any galaxy in the sky. NGC 1277 orbits not far from this behemoth, astronomically speaking just a stone's throw away within the cluster's core region. Normally, smaller galaxies that wander too close to giants like NGC 1275 are either absorbed through mergers or stripped of their stars and gas through gravitational tides. Yet NGC 1277 remains intact, compact, and undisturbed. This survival hints that its orbit through the cluster has been unusually fortunate, keeping it clear of catastrophic encounters. One of the key ways galaxies interact in clusters is through ram pressure stripping. As a galaxy speeds through the dense intracluster medium, the hot plasma acts like a headwind, blowing away any cold gas. This process is thought to have robbed NGC 1277 of the raw material needed for star formation billions of years ago. While most galaxies might replenish that gas through mergers with smaller companions, NGC 1277 avoided such interactions. The result was a 1-2 punch, stripped of its gas by the cluster environment and never refueled by new mergers. This sealed its fate as a relic. Interactions with neighbors can also warp or distort galaxies, leaving visible scars in the form of tidal tails, bridges, or disrupted structures. High-resolution images of NGC 1277 show none of these features. Its light profile is smooth, symmetrical, and compact. That means either it has avoided close passes with its cluster companions, or it is so tightly bound that it resisted deformation. Either way, its clean profile is striking in an environment where chaos is common. Astronomers have also considered whether NGC 1277 might once have been part of a larger galaxy that was stripped down by cluster interactions, leaving only its dense core. While this could, in theory, explain its compactness, the uniform age of its stars argues against it. A stripping event would likely have left behind a mix of stellar populations, including some younger ones. Instead, NGC 1277's stars all appear to have formed in a single early burst. This points not to a stripped remnant, but to a fossil galaxy that simply never grew. Its relationship with neighbors also extends to gravitational dynamics. Within the Perseus Cluster, galaxies orbit within a shared dark matter halo. NGC 1277's orbit may have carried it in such a way that it avoided the most destructive interactions. While many cluster galaxies fell into the central region and merged with NGC 1275, NGC 1277 seems to have skirted the worst of the violence, maintaining its identity across cosmic time. This is remarkable given how long it has been part of the cluster environment. Another intriguing angle is the comparison between NGC 1277 and other compact relics in similar clusters. A few have been found, such as MRK 1216 and NGC 1271, that also survived without major interactions. These galaxies suggest that relics like NGC 1277 may share a common trait: orbits or environments that shield them from disruption, while still exposing them to the stripping forces that end star formation. In other words, they avoid mergers, but not quenching. This balance leaves them fossilized, but intact. It is also worth noting that despite living in the same cluster, NGC 1277 looks nothing like its flamboyant neighbor NGC 1275. Where NGC 1275 is an active galaxy with jets, glowing gas filaments, and evidence of recent interactions, NGC 1277 is a silent relic, featureless and compact. Together, they represent opposite ends of the galactic evolutionary spectrum, one constantly changing and active, the other frozen in time. Their coexistence within the same cluster underscores the diversity of pathways galaxies can take, even when exposed to the same larger environment. The relationship between NGC 1277 and its neighbors also helps explain why astronomers call it a relic galaxy. It is not just the age of its stars or the size of its black hole. It is the fact that in a cluster teeming with mergers and transformations, this one galaxy has remained virtually untouched. That makes it both rare and scientifically invaluable. By comparing it to its more evolved neighbors, astronomers can see what has been preserved and what has changed in galaxy evolution across billions of years. In short, NGC 1277's survival in the Perseus Cluster is nothing short of extraordinary. It has lived next to one of the most active galaxies in the universe without being consumed. It has avoided the mergers that built up its peers. It has been stripped of its fuel but left structurally intact. In a cluster where most galaxies bear the scars of violent interactions, NGC 1277 stands out as a pristine fossil, an ancient survivor in a crowded cosmic city. But the big question remains, if NGC 1277 missed the usual growth phases through mergers and accretion, what exactly does that tell us about the broader story of galaxy formation? Evidence that it missed the usual growth phase. In the story of galaxy evolution, growth is the rule. Small, compact galaxies from the early universe almost always balloon into larger systems through mergers and accretion, becoming the grand ellipticals and spirals we see today. But NGC 1277 is an exception. The evidence suggests it completely skipped that growth phase, freezing in a compact fossil-like state. For astronomers, this missing chapter in its life story is what makes it such a valuable relic, an unaltered glimpse into what galaxies looked like 10 billion years ago. The first line of evidence is its size. Early galaxies, the so-called red nuggets, were compact and dense. Over billions of years, they grew larger through collisions with neighbors, absorbing their stars and expanding their halos. Modern giant ellipticals are the descendants of these nuggets. But NGC 1277 is still only about 10,000 light-years across, 1/10 the diameter of the Milky Way. It never grew into a giant elliptical, suggesting it bypassed the mergers that drive that transformation. The second clue lies in its stellar population. Spectroscopy reveals that nearly all of NGC 1277 stars formed over 10 billion years ago in a single, intense burst of star formation. In galaxies that grew through mergers, you find multiple generations of stars, with some younger populations sprinkled in. Not here. NGC 1277 is composed almost entirely of ancient metal-rich stars. This uniformity is a clear signal that it didn't experience the fresh infusions of gas and stars that mergers usually deliver. Another piece of the puzzle is the lack of cold gas. Galaxies typically replenish their star-forming fuel when they collide with others, or accrete gas from the cosmic web. That new gas reignites star formation, keeping the galaxy alive and evolving. NGC 1277 has no such reservoir. Observations in radio and millimeter wavelengths show that it is barren of molecular hydrogen, the raw material for new stars. This means not only did it stop forming stars early, it never restarted. Without mergers to provide fuel, the galaxy remained sterile. The absence of structural features further supports this picture. Galaxies that grow through mergers often develop extended halos, tidal streams, or disrupted shapes from gravitational encounters. NGC 1277 is smooth and compact, showing no signs of such interactions. Its surface brightness profile falls steeply, with most of its light concentrated at the center. This profile is identical to compact ellipticals from the early universe, reinforcing the idea that it hasn't changed since then. Its relationship with the Perseus Cluster also tells part of the story. In such a crowded environment, galaxies are constantly colliding and reshaping each other. NGC 1277's survival as a compact fossil suggests it somehow avoided this fate. Perhaps its orbit through the cluster kept it away from the most chaotic regions, sparing it from mergers that would have grown it. While many cluster members became giants through repeated collisions, NGC 1277 stayed small, retaining its red nugget form. One of the strongest arguments that it missed the growth phase is its black hole to stellar mass ratio. In most galaxies, black hole growth and galaxy growth keep pace. Mergers not only add stars, but also deliver gas that feeds black holes, keeping the balance relatively stable. In NGC 1277, the black hole grew early and then stopped, while the galaxy itself never added enough stars to match. This imbalance suggests the galaxy missed out on the mergers that should have brought in more stellar mass. Without that growth, the black hole remained proportionally overmassive. Simulations back up this conclusion. Computer models of galaxy evolution show that if a compact galaxy avoids mergers after about redshift 2, roughly 10 billion years ago, it will remain small and dense, looking like a relic today. NGC 1277 fits this prediction perfectly. Its current size, stellar population, and lack of gas all match the simulations of galaxies that skipped the usual growth track. Another subtle piece of evidence comes from its dark matter content. Recent studies suggest that NGC 1277 may be unusually poor in dark matter compared to other galaxies. If true, this could explain why it never accreted enough material to grow. Dark matter halos act like gravitational nets, pulling in gas and small galaxies. Without a large halo, NGC 1277 might have missed the chance to capture fuel and companions, leaving it locked in its original compact state. The missing growth phase is what makes NGC 1277 so important scientifically. Most galaxies in the nearby universe are too contaminated by later events to tell us much about their early history. Mergers and starbursts blur the record of their formation. NGC 1277, by contrast, is a clean fossil. By studying it, astronomers can directly measure what galaxies looked like at the end of their first major growth spurt, before billions of years of mergers rewrote their histories. In essence, NGC 1277 missed out on the galactic equivalent of adolescence and adulthood. It had a brilliant, fiery youth, forming all its stars and ballooning its black hole quickly. But then it skipped the growth phase, settling into a static old age that has lasted ever since. That skipped chapter is what makes it both anomalous and invaluable. A galaxy that froze at a stage most others outgrew long ago. But the implications go further. If NGC 1277 really is a fossilized relic, then it tells us something about the early universe itself. What it reveals about early galaxy formation. NGC 1277 is more than a curiosity. It is a Rosetta Stone for understanding how galaxies formed in the earliest epochs of the universe. Because it has remained largely unchanged for more than 10 billion years, it offers astronomers a rare chance to study conditions that were once common, but are now almost extinct. By examining NGC 1277, we gain insights into the processes that shaped galaxies during cosmic dawn, when the universe was only a fraction of its current age. One of the most important revelations is that galaxies in the early universe were far more compact and dense than those we see today. Observations of high redshift galaxies, those seen as they were billions of years ago, show small spheroid-shaped systems only a few thousand light-years across. These so-called red nuggets were everywhere around 10 billion years ago, but most of them grew larger through mergers. NGC 1277 shows us what one of those nuggets looks like up close, frozen in time. Instead of studying faint smudges billions of light-years away, astronomers have a nearby fossil to examine in detail. The stellar populations of NGC 1277 also tell us about the intensity of early star formation. Spectroscopy reveals that nearly all its stars were formed in a short, violent burst more than 10 billion years ago. This rapid buildup of mass mirrors what we see in distant galaxies from the same era, when gas collapsed efficiently to produce dense stellar systems. The chemical makeup of its stars, rich in heavy elements, indicates that supernovae enriched the galaxy quickly, leaving a uniform population behind. By studying NGC 1277 stars, astronomers can reconstruct the pace and scale of early universe starbursts. The monster black hole at its center provides another crucial clue. In the early universe, we see quasars powered by billion solar mass black holes only a few 100 million years after the Big Bang. How could black holes grow so large, so fast? NGC 1277 offers a local example of this phenomenon. Its black hole appears to have ballooned rapidly during the first billion years, outpacing the growth of the galaxy around it. That suggests that early universe conditions allowed black holes to grow explosively, perhaps by feeding on massive reservoirs of cold gas or by forming from unusually heavy seeds. NGC 1277 is the fossil evidence that such runaway growth really happened. The lack of later star formation in NGC 1277 also reveals how feedback processes shaped galaxies. Once its black hole reached a certain size, it likely began expelling or heating the gas that would have formed new stars. This self-regulating process, where black holes prevent further galaxy growth, appears to have been active even in the earliest galaxies. NGC 1277 froze at an early stage because its black hole locked it there. This shows that feedback isn't just a modern mechanism. It has been shaping galaxies for most of cosmic history. Another key lesson is about diversity in galaxy evolution. Most red nuggets from the early universe didn't remain compact. They merged, expanded, and evolved into giant ellipticals. But a few, like NGC 1277, missed that pathway and stayed small. This tells us that the universe doesn't enforce a single script for galaxy growth. There are multiple evolutionary tracks, and relics like NGC 1277 represent the rare ones that diverged. They are natural experiments, showing what happens when galaxies skip the usual growth phases. NGC 1277 also informs our understanding of the cosmic timeline. Because it is unchanged, it locks in the conditions of galaxy structure around redshift 2, about 10 billion years ago. Astronomers can compare its properties to galaxies seen at that redshift with telescopes like Hubble and JWST. The similarities confirm that our models of early galaxies are accurate. It validates that the compact, dense systems we see in the distant universe are indeed the ancestors of today's massive ellipticals, except in rare cases like NGC 1277, where evolution froze. Its environment within the Perseus Cluster adds another layer of insight. Normally, cluster environments accelerate galaxy evolution through mergers and stripping, yet NGC 1277 managed to survive intact. This suggests that relic galaxies can act as control samples for understanding what early galaxies were like before cluster dynamics reshaped them. They are rare precisely because surviving in such environments is difficult, making each discovery scientifically precious. In essence, NGC 1277 reveals that early galaxy formation was fast, intense, and varied. Galaxies like it formed their stars and black holes quickly, then followed very different paths depending on their environments. Most grew and changed, but a few remained locked in their original state. For astronomers, this provides a window into the before picture, a glimpse of what the universe looked like before billions of years of mergers blurred the story. The galaxy's very existence tells us that fossils of the early universe can still be found nearby. They are needles in the haystack of modern galaxies, but each one is a time machine. By studying NGC 1277, scientists are effectively reaching back across cosmic history, holding in their hands a relic of a time when the universe was just beginning to build its grand structures. How relic galaxies differ from normal ellipticals. At first glance, NGC 1277 looks like just another elliptical galaxy. It has the same smooth oval profile, no spiral arms, no dust lanes, and no obvious signs of ongoing star formation. But beneath the surface, it is radically different from the massive ellipticals we see elsewhere in the universe. Relic galaxies like NGC 1277 are the untouched fossils of cosmic history, while normal ellipticals are the products of billions of years of growth and mergers. Understanding the differences between them is crucial for placing NGC 1277 in its proper context. The most obvious difference is size. Normal elliptical galaxies are huge, often spanning tens or even hundreds of thousands of light-years across. They contain not just dense cores, but also extended halos of stars that stretch far into space. NGC 1277, by contrast, is compact, barely 10,000 light-years wide. It is the bare nucleus of what an early elliptical would have looked like, without the extended structure added by billions of years of mergers. In effect, normal ellipticals are bloated descendants, while relics like NGC 1277 are the before snapshot. Another major difference lies in their stellar populations. Normal ellipticals host stars of a wide range of ages. Although many are dominated by older stars, mergers and accretion events can bring in younger populations, creating a layered history that astronomers can read through spectroscopy. Relic galaxies, on the other hand, are made almost entirely of ancient stars. In NGC 1277, over 90% of its stars are more than 10 billion years old. There is no evidence of later waves of star formation. This uniformity is one of the hallmarks of a relic galaxy, and one of the clearest distinctions from its evolved cousins. The black hole to galaxy mass ratio is another key separator. In normal ellipticals, the central black hole is massive but proportional. Typically, it makes up about 0.1% of the galaxy's stellar mass. In NGC 1277, the black hole makes up 10–14%. That difference of 2 orders of magnitude is unheard of in normal ellipticals. The imbalance underscores how relic galaxies froze at a stage where the black hole had already grown huge, but the host galaxy never caught up. In ordinary ellipticals, mergers added stars and gas over time, restoring the balance. Relic galaxies also differ in their structure and morphology. Normal ellipticals have extended outer envelopes, often with faint shells, tidal streams, or halos left over from past mergers. These features reveal their dynamic histories, showing that they were built through repeated collisions. NGC 1277 has none of these. Its light falls off sharply with radius, with almost all its stars packed tightly into the core. It is smooth and featureless, with no signs of tidal debris. This lack of scars is evidence that it has avoided the mergers that shaped ordinary ellipticals. Gas and dust content provide another distinction. Normal ellipticals, especially those that grew large in clusters, often retain small amounts of hot gas. Some even have residual cold gas, fueling low levels of star formation. Relic galaxies like NGC 1277 are barren. Radio and millimeter observations reveal almost no cold gas, and infrared surveys show little dust. They are sterile fossils, long since stripped of the ingredients needed to form new stars. This sterility makes them relics, galaxies that ended their evolution early and never restarted. The environments of relics and normal ellipticals also highlight differences. Normal ellipticals tend to dominate clusters, sitting at the centers where they cannibalize smaller galaxies and grow over time. NGC 1277 is unusual in that it lives in a cluster but has somehow avoided this growth path. Its survival as a compact fossil in the Perseus Cluster suggests it followed an orbital path that kept it out of the central feeding grounds. In this way, it is an exception. Most galaxies in its environment grew large through mergers, while it stayed small and untouched. There are also differences in dark matter content. Normal ellipticals are embedded in massive dark matter halos that help stabilize their structure and pull in new material. NGC 1277 appears to have less dark matter than expected for its size. This could explain why it failed to grow. Without a strong dark matter halo to capture gas and small galaxies, it remained compact. This contrasts sharply with the vast halos of normal ellipticals, which facilitated their growth. In terms of dynamics, normal ellipticals are pressure-supported systems, with stars moving in random orbits rather than orderly rotation. Relic galaxies share this trait, but in NGC 1277, the effect is amplified by the dominance of its central black hole. The stars move at extreme velocities across a compact volume, making the entire galaxy feel like a scaled-down but intensified version of a normal elliptical. Finally, the scientific role of relics versus normal ellipticals is different. Normal ellipticals tell us about the cumulative effects of billions of years of cosmic history, how mergers shape galaxies, how black holes grow steadily, and how environments sculpt structure. Relics, by contrast, are fossils of the universe's youth. They tell us what galaxies were like before the mergers, before the gradual expansion, before the modern era. Studying both gives astronomers a before and after picture of galaxy evolution. In short, normal ellipticals are the products of long, messy histories, while relic galaxies like NGC 1277 are untouched survivors of the early universe. They are smaller, denser, older, and more extreme, with black holes that outweigh their stellar populations far beyond the norm. The contrast between the two is what makes relics so important. They are not just unusual, they are windows into a time when all galaxies looked like this. But observing relics isn't easy. Their compactness and distance make them difficult to study, requiring the sharpest instruments in astronomy. Up next, we'll dive into the observational challenges of studying NGC 1277 and why proving its extreme nature was no simple task. Observational challenges in studying NGC 1277. NGC 1277 is often described as one of the most extraordinary galaxies ever studied, but proving its unusual properties was not easy. From its compact structure to its overmassive black hole, every conclusion required years of careful observation and advanced techniques. At a distance of roughly 220 million light-years, NGC 1277 is close enough to study in detail compared to galaxies billions of light-years away, yet still far enough that its compactness and faint features push the limits of our instruments. The path to confirming its relic status was filled with technical hurdles, uncertainties, and debates. Resolution is one of the hardest things to do. It's not very big. NGC 1277 is only 10,000 light-years across. That is the same as a very small angle in the sky, only a few arc-seconds wide. To see its heart, which is where the black hole's effects are biggest, you need very clear pictures. The atmosphere of Earth blurs the red light from ground-based cameras, making it difficult for them to see such small details. So, scientists rely on the Hubble Space Telescope a lot. It orbits above the Earth's atmosphere and can provide the clear images needed to follow the light profile of the galaxy. Without Hubble, it would have been very hard to get a good reading on how dense the bulge was. Another difficulty is measuring stellar motions. The key to estimating the black hole's mass lies in tracking how fast stars move near the center. But at NGC 1277's distance, these stars blur together into a single glow of light. Astronomers can't track individual stars like they do around Sagittarius A star in the Milky Way. Instead, they have to rely on spectroscopy, analyzing the combined starlight to measure Doppler shifts that reveal the average velocities of stars in different regions. This requires high signal-to-noise data and extremely sensitive instruments. Even then, uncertainties in the models can lead to large differences in the inferred black hole mass. The lack of gas makes things even more difficult. Astronomers find out how heavy black holes are by following gas rings around the core of some galaxies. These gas rings show the effect of gravity in a clean, bright way. But NGC 1277 is empty. It doesn't have any cold gas, bright emission lines, or easy-to-find tracers going around the black hole. It was only left to figure out how the stars move, which is harder to do. Stellar circles are random and asymmetrical, which means they don't all go in a circle. Complex dynamical modeling is needed to figure out how to measure the mass of these movements. These models themselves add another layer of uncertainty. Astronomers use Jeans equations and orbit-based models to simulate the galaxy's dynamics and fit them to the observed velocity dispersions. But assumptions about the distribution of dark matter, the anisotropy of orbits, or the galaxy's shape can all change the final number. This is why the first study in 2012 reported a black hole of 17 billion solar masses, while later reanalyses suggested closer to 12 billion. Both are extreme, but the range shows how sensitive the results are to model choices. Even measuring the dark matter content of NGC 1277 posed challenges. In normal galaxies, dark matter halos are inferred from the motions of stars and gas at large radii. But NGC 1277 is so compact, with most of its stars packed tightly near the center, that disentangling the dark matter contribution is nearly impossible. Some studies suggest it has very little dark matter, while others argue the models can't rule out a normal halo. The debate over its dark matter content remains unresolved, largely because of these observational limitations. The discussion in the astronomical world was another problem. The first report of a 17 billion solar mass black hole in such a small galaxy was met with doubt because it was based on very weak data. Critics said that if the velocity dispersions were overestimated or the stellar mass was underestimated, it could make the black hole look bigger than it really is. It took several follow-up tests to prove that, even though the exact number could change, the black hole was definitely too huge. Part of the reason NGC 1277 has become such an important object in the field is that it drove astronomers to improve their methods and test the limits of their equipment. The cluster environment also adds complications. NGC 1277 sits in the crowded Perseus Cluster, where the light from neighboring galaxies can interfere with measurements. Distinguishing NGC 1277's faint outer light from the glow of nearby galaxies requires careful image processing and subtraction techniques. Without precise handling of this contamination, estimates of its size, brightness, and structure could be skewed. Use of integral field spectroscopy in its analysis. Scientists needed more than clear pictures to get a good idea of how big the black hole inside NGC 1277 was, so they could make a picture of how the stars moved across the sky in 2 dimensions, not just along one line of sight. This is where integral field spectroscopy, IFS, came in handy. It is an important part of the story of NGC 1277's monster black hole. Traditional spectroscopy collects light from a single slit across the galaxy, producing a one-dimensional spectrum. While useful, this method only reveals velocities along that narrow strip. For compact galaxies like NGC 1277, where every fraction of an arcsecond matters, that's not enough. Integral field units, IFUs, revolutionize the field by breaking the incoming light into a grid of tiny elements, each with its own spectrum. The result is a data cube, 2 spatial dimensions plus 1 spectral dimension. It allows astronomers to construct a full velocity map of stars across the galaxy, showing how fast they are moving and in what direction. For NGC 1277, this was essential. Observations with IFU instruments such as OSIRIS at the Keck Observatory and the spectrograph for integral field observations in the near-infrared, SINFONI, on the Very Large Telescope gave astronomers detailed velocity fields. These maps revealed steep velocity gradients near the core, where stars orbit at hundreds of kilometers per second. Without IFS, the extreme rise in stellar speeds close to the center might have been missed or underestimated. IFS is very good at measuring velocity dispersion, which is how much the speeds of stars change in different directions. The spread in NGC 1277 was huge, much bigger than what you'd expect for a galaxy that size. These differences in speed could not be explained by the stars that can be seen by themselves. A black hole the size of billions of suns was the only answer that made sense. IFS also helped measure the anisotropy of stellar orbits. In galaxies, stars can move in more ordered, rotating patterns or in random, pressure-supported motions. By mapping the line-of-sight velocities across NGC 1277, astronomers found that it lacked significant rotation. The stars move chaotically, consistent with a dense elliptical structure dominated by central gravity rather than disk-like organization. This confirmed that NGC 1277 is a compact elliptical relic rather than a stripped spiral or other type of galaxy. Another good thing about IFS is that it lets scientists separate the effects of stars, dark matter, and the black hole. Scientists could make models of how the galaxy moves by putting together the light profile from Hubble and the motion maps from IFS. The following situations were tested by these models. Should the stellar mass be enough to explain the speeds? Could the dark matter in the middle make up the difference? A black hole with billions of solar masses is consistently the best fit. For orbit-based models, IFS also gave the data that was needed. With these advanced methods, you can fake thousands of possible stellar paths inside the galaxy and then compare them to the velocity maps that have already been seen. Astronomers find the most accurate mix by changing things like black hole mass, stellar distribution, and orbital anisotropy. Even when modest estimates were used, the models always showed that NGC 1277 had a black hole that was much bigger than what was expected. The use of IFS also reduced some of the uncertainties that plagued earlier measurements. Long-slit spectroscopy could overestimate velocity dispersions if the slit happened to cut through a particularly dense region. By mapping the whole core, IFS ensured a more balanced picture. That's one reason later studies revised the black hole mass downward from 17 billion to about 12 billion solar masses. But even at the lower figure, the black hole remained massively oversized. The precision of IFS didn't erase the anomaly, it confirmed it. Tech was also put to the test with NGC 1277. Adaptive optics helped instruments like Keck's OSIRIS get a clearer picture by adjusting for changes in the atmosphere in real time. They had the best chance to look into the heart of the galaxy when they used adaptive optics and IFS together. The results showed that these kinds of methods could very accurately measure black holes in galaxies that are far away and close together. IFS is now thought to be one of the best methods for determining the mass of a black hole in the red. Scientists were inspired to look for other ghost galaxies after using IFS on NGC 1277. If such a big black hole can be found in one small oval, then maybe others can too. In fact, later studies using the same methods found galaxies like MRK 1216 and NGC 1271 to be more old objects with huge black holes. There might not have been any searches for these things without the first ever use of IFS on NGC 1277. Simulations of its possible history. Experts use simulations to figure out how NGC 1277 became such a strange object. Observations can tell us what it looks like now. These computer models show how gas, stars, dark matter, and black holes interact with each other based on the rules of physics over billions of years. Scientists can try out different evolutionary models and see which one best fits the strange traits of NGC 1277 by comparing the results of the simulations to the real thing. Among the most basic theories starts with the idea that NGC 1277 is a red nugget that has still been around. In this version, the galaxy formed very quickly in the early universe. Gas collapsed into a tight, compact core that made stars and a giant black hole all at once. In later years, most red nuggets got bigger through mergers, but NGC 1277 didn't go through this phase of growth. Simulators that follow galaxies from a time of high redshift to now show that, even though they are rare, some bits can live mostly unaltered. They stay small, with old stars and black holes that are too big for their surroundings, just like NGC 1277. Other simulations explore the idea of early runaway black hole growth. In these models, conditions in the early universe allowed some black holes to grow explosively, consuming gas faster than their host galaxies could replenish it. Feedback from this rapid growth then quenched star formation, halting the galaxy's development. The result is a compact, fossil-like system with a disproportionately large black hole. This fits neatly with NGC 1277's observed imbalance, where the black hole makes up an astonishing fraction of the galaxy's total mass. A different type of simulations checks to see if NGC 1277 could be the remains of a galaxy that was taken away. When galaxies are close together, like in Perseus, gravitational tides often pull them apart. A bigger galaxy might lose its gas and stars on the edges to the cluster environment, leaving only its small core. A piece of that would look a lot like NGC 1277 does now, small, dense, and controlled by a huge black hole. NGC 1277 does not have any structural scars or mixed stellar populations, as predicted by modeling of this process. Its stars are all very old, which suggests that it wasn't taken but rather kept. Still, the stripped core situation is still an option that has been talked about in the literature. Cosmological simulations like Illustris and Eagle have also been used to look for analogues of NGC 1277. These massive computer projects simulate large volumes of the universe, tracking the formation of thousands of galaxies. In these virtual universes, relics do occasionally appear. Galaxies that formed early, quenched quickly, and then survived untouched. They are rare, making up only a small fraction of all galaxies, but their existence supports the idea that NGC 1277 is not unique. It is one of a rare breed, a survivor of an evolutionary path most galaxies abandoned. Simulations also help explain NGC 1277's puzzling dark matter content. Some studies suggest it has far less dark matter than expected for a galaxy of its size. In simulations, this can happen if a galaxy forms in a particularly dense cluster environment, where tidal interactions strip away its dark matter halo over time. If NGC 1277 lost much of its halo early on, that could explain its compactness and why it never accreted new material to grow. In this view, the galaxy isn't just a relic, it is a relic that was pruned by its environment. The path that NGC 1277 has taken around the Perseus Cluster is another important view. Simulations show that galaxies and clusters move in different ways around the center. Some fall into the center and get smashed, while others stay on safer, farther away paths. If NGC 1277 had a path that was pretty stable and kept it from hitting anything big, that might explain how it managed to stay alive. The right path in the right place at the right time might be a good way to describe its past. Simulations also explore the role of feedback from the central black hole. When black holes accrete matter, they can unleash enormous outflows of energy. In some models, NGC 1277's black hole may have quenched the galaxy early by blasting out its gas. Without gas, the galaxy stopped forming stars and never grew further. The feedback mechanism essentially froze the galaxy in place, locking it into the relic state we observe today. This idea fits with the fact that NGC 1277's stars are ancient and no fresh star formation has occurred since. Alternative explanations for its properties. When scientists see something as strange as NGC 1277, they naturally become skeptical. Could the sizes not be right? Could the galaxy's strange features be caused by something less strange than a supermassive black hole and a structure frozen in time? Several different theories have been put forward over the past 10 years. Even though none of them have completely disproved the idea that NGC 1277 is an old galaxy ruled by a huge black hole, they do show how hard it is to study systems that are so far away and so close together. The most debated issue is the true mass of the black hole. When Remco van den Bosch's team first published their results in 2012, they estimated the mass at 17 billion suns, making it one of the largest ever recorded. Critics quickly pointed out that this estimate relied heavily on assumptions in the stellar dynamical models. For example, the distribution of stellar orbits, whether stars move more randomly or in ordered paths, can significantly change the inferred black hole mass. If the models assume too much anisotropy, the mass can be overestimated. Follow-up studies refined the black hole's mass downward to around 12 billion suns. Still enormous, but not quite as extreme. Others suggested it could be as low as 5 billion, depending on model assumptions. Even at the low end, however, the black hole is disproportionately large for the galaxy. The debate shows that while the exact number may shift, the fundamental anomaly remains, whether it is 5, 12, or 17 billion. The black hole is far too big for its host, keeping NGC 1277 firmly in the overmassive category. The stripped galaxy situation is another possible answer. From this point of view, NGC 1277 may have been a much bigger galaxy in the past, with layers of stars and dark matter that stretched out to the edges. Over billions of years, the outer parts of the Perseus Cluster may have been ripped away by gravity pulls and ram pressure stripping, leaving only the dense core. That core would naturally have a lot of huge black holes and packed stars, just like the ones we see now. While appealing, the stripped core idea has weaknesses. Stripping usually leaves scars, tidal tails, asymmetries, or shells of debris, but NGC 1277 shows none of these. Its stars are uniformly old, with no evidence of younger populations that mergers might have introduced. If it was stripped, it must have happened very early, before any major growth occurred, leaving a relic that looks virtually unchanged for 10 billion years. In that case, the stripped galaxy and relic galaxy scenarios begin to blur into one. Analysts have also said that the results might not be what they seem to be because of how the dark matter is distributed. If NGC 1277 has a dark matter halo that isn't like most, then models that assume a normal halo might overestimate the black hole's mass to make up for it. By looking at what has been seen, NGC 1277 may be missing dark matter compared to other galaxies the same size. This makes it more likely that the strange way it moves isn't just because of the black hole, but also because its ring doesn't have enough mass that we can see. Even so, the black hole still looks a lot bigger than anyone thought it would be. It's also possible that we are seeing impacts of imagination. Galaxies are three-dimensional, but we see them as flat pictures in the sky, so their speeds and forms can be misunderstood. The speed differences we measure might be too small to fully describe the black hole's gravitational pull if NGC 1277 is oriented in a certain way, or if its stars move on very long orbits. This is tried to be fixed by more complicated orbit-based models, but the level of detail still leaves room for argument. Some have even wondered whether NGC 1277 might be an intermediate mass system caught in transition. Perhaps it began as a red nugget, started to grow, but had its evolution halted by the cluster environment. If so, it would not be a pristine relic, but a failed elliptical, stuck halfway through its development. This hybrid scenario could explain its compactness and old stars, while also acknowledging that it lives in a dynamic cluster where complete isolation is unlikely. Even with these other ideas, the core proof won't budge. The stars in NGC 1277 are very old, the galaxy is not very big, and the black hole inside it is wildly out of scale. The numbers might be changed by stripping, projection effects, or modeling errors, but they can't get rid of the basic oddity. There is only one way to end each scenario. This is not a standard world. NGC 1277 doesn't fit any of the other names for it, like a bare core, a rare red nugget, or just a relic. Other known relic galaxies for comparison. For many years, NGC 1277 was thought to be the only galaxy in the universe with a black hole that was so big that it seemed to be out of place. But as scientists got better at observing and started looking for more leftovers on purpose, a few cousins started to show up. A lot of the strange things about these galaxies are the same. They are small, they have black holes that look too big for their hosts, and their stellar populations are very old. To get a better idea of what ghost galaxies are, how they form and how uncommon they really are, scientists can compare them to NGC 1277. MRK 1216 is one of the most well-known. MRK 1216 is about 300 million light-years away and is often called NGC 1277's twin. It is small and close together, just like its cousin. Its width is only about 10,000 light-years. It is home to a supermassive black hole that weighs about 4.5 billion suns, which is huge in comparison to its red stellar mass. Spectroscopy shows that all of its stars are the same age and were formed in a single starburst more than 10 billion years ago. MRK 1216 is basically a red nugget that never grew. This is proof from a different source that galaxies like NGC 1277 are not one-of-a-kind events, but rather a small group of survivors. NGC 1271 is another example. It is in the same group as NGC 1277 and is also a star cluster. Compared to other ellipticals, NGC 1271 is a bit bigger, but still pretty small. Its black hole in the middle is about 3 billion times the mass of the Sun, which is quite large compared to the galaxy around it. Since NGC 1271 and NGC 1277 are both in the same cluster, it seems likely that Perseus is a particularly good place to keep artifacts safe. It means that sometimes cluster dynamics can let compact galaxies stay alone for billions of years, even in settings that are very unstable. Moving farther afield, there is PGC 032873, another compact elliptical with an oversized black hole. Though less well studied than NGC 1277 or MRK 1216, it shows the same general features: old stars, small size, and an outsized central mass. Each new discovery reinforces the idea that relic galaxies are a real population, not just one-off anomalies. What unites these galaxies is their shared evolutionary path. They formed rapidly in the early universe, producing dense cores and massive black holes in record time. Then, unlike most galaxies, they avoided the mergers and gas accretion that would have grown them larger. The result is a fossilized population of red nuggets surviving into the modern era. Comparing multiple relics allows astronomers to rule out explanations that depend only on NGC 1277's specific circumstances. For example, the stripped core scenario is harder to defend when multiple galaxies show the same features without evidence of stripping. There are some changes that are worth pointing out, even though they are identical. NGC 1277 has a bigger black hole compared to its stellar mass, but MRK 1216's is still very big. This points to a range of relic galaxies, with some being more extreme than others. In NGC 1277, the black hole is responsible for up to 14% of the galaxy's stellar mass, making it the most interesting case. The numbers are lower in MRK 1216 and NGC 1271, but they are still much higher than average. Astronomers can use this range as a test bed to see how different levels of imbalance change the formation of galaxies. The places where relic galaxies are located are also different. NGC 1277 and NGC 1271 are part of the dense Perseus Cluster, but MRK 1216 is more spread out. This difference shows that relics can live in a lot of different situations. To stay alive in a cluster, it may rely on lucky orbits that keep big crashes from happening. When someone is alone, it might just be that they don't have any friends to join with. In the end, both tracks lead to the same place, a small fossilized galaxy ruled by an old black hole. The rarity of these galaxies is another important point. Surveys suggest that only about 1 in 1,000 massive galaxies in the local universe are relics. That makes them statistical outliers, but not impossibilities. Their rarity is part of what makes them scientifically valuable. They are snapshots of an evolutionary stage that almost every other galaxy moved past. Each relic discovered adds to the evidence that the early universe produced many more red nuggets than survive today. Role of environment in relic survival. Relic galaxies rely on the galaxies nearby to stay alive if they are fossils from the early universe. The atmosphere a galaxy lives in can affect whether it changes over billions of years through mergers and accretion, or stays the same. In order to understand why NGC 1277 and its relatives exist, the importance of their environments is very important. The Perseus Cluster, where NGC 1277 resides, is one of the densest cosmic environments nearby. It contains thousands of galaxies orbiting within a massive dark matter halo filled with hot intracluster gas. Normally, such a setting is hostile to small galaxies. Interactions, stripping, and mergers are the norm. Many galaxies in clusters grow by cannibalizing their neighbors, while others are stripped down to ghostly remnants. The fact that NGC 1277 survived here as a compact relic is surprising. It suggests its particular orbit and location within the cluster shielded it from the worst of this chaos. NASA scientists think that the climate affects the life of relics in two different ways. On the one hand, thick groups make stripping and cooling easier. Ram pressure stripping takes away gas as galaxies move through the hot medium inside the cluster, which stops star formation early. As a result, galaxies with old stellar populations look like they're from the past. On the other hand, clusters also cause galaxies to join, which makes them bigger and less packed. A treasure must go through the first process without dying in the second one in order to stay alive. It looks like NGC 1277 lost its gas early on and didn't join with any other galaxies, which would have made it bigger. Some relics, like MRK 1216, are found in places that are not connected to anything else. There were never many galaxies nearby for these to crash into each other. In these situations, their ability to stay alive is due to the lack of contacts. They stayed small and preserved because they didn't have any other creatures to merge with. That's proof that relics can survive in a variety of environments. A galaxy can stay in its original state by being alone or in a carefully safe path within a cluster. It's also because of the surroundings that relics are so hard to find. Simulations show that less than 1% of galaxies in the universe today are real old ones. Most of the time, galaxies either grew by merging or died by interacting with other galaxies. An old galaxy has to walk a fine line between being stripped down enough to stop star formation and merging too much to get bigger. This fine balance is much harder to keep in groups, where big crashes are more likely to happen. That makes it even more amazing that NGC 1277 is still there in Perseus. Another environmental factor is the cluster's gravitational potential. In the dense core of Perseus, many galaxies spiral inward and are eventually consumed by NGC 1275, the central giant. If NGC 1277 had been on such a trajectory, it would not exist today. Instead, it seems to orbit farther out, where tidal forces are weaker and mergers less frequent. Its survival may be partly due to luck, landing in the right orbit billions of years ago. The environment may also explain NGC 1277's puzzling dark matter content. Studies suggest it has less dark matter than expected, perhaps because cluster interactions stripped away much of its halo. Without a large halo, NGC 1277 could not accrete fresh gas or capture smaller galaxies. That may have locked it into its compact state, preventing growth. In this sense, the cluster both harmed and helped, stripping away the potential for evolution while simultaneously preserving the relic core. A pattern shows up when you look at relics from different places. Cluster relics like NGC 1277 and NGC 1271 are more extreme, with black holes that are very big and almost no dark matter. Some relics like MRK 1216 that are kept alone are less stripped but still frozen. This shows that a relic's surroundings determine its exact shape, but its core nature, compact, old and ruled by old stars, doesn't change. Foreground and background contamination in observations. To get a good look at NGC 1277, you can't just point a telescope at the Perseus Cluster and collect light. The galaxy lives in a cosmic city with a lot of other galaxies. It is ringed by thousands of other galaxies and soaked in the warm medium between the clusters. This makes center and background pollution one of the hardest things to see. Astronomers have to take great care to separate the light of NGC 1277 from that of its neighbors in order to get accurate measurements of its structure, stellar population, and black hole. NGC 1275 is the largest and most active galaxy in the Perseus Cluster. It has bands of burning gas that stretch over tens of thousands of light-years. NGC 1277 is pretty close to this powerhouse in the sky. The scattered light and filaments from NGC 1275 spill into the same area, making NGC 1277's appearance too bright. If this problem isn't fixed, it could make NGC 1277 look brighter or bigger than it really is, which would change predictions of how big and heavy it is. To find NGC 1277's true light, astronomers have to model and remove NGC 1275's input. Foreground stars in our own Milky Way add another complication. The Perseus Cluster lies in a field scattered with faint stars that overlap with galaxies in images. For NGC 1277, even a single bright star projected against its compact disk can distort measurements of its surface brightness profile. High-resolution imaging from the Hubble Space Telescope helps distinguish point sources, stars, from the smooth glow of the galaxy. Once identified, the stars can be masked or subtracted, but the process requires painstaking precision. Background galaxies can also intrude. The line of sight to Perseus cuts through the distant universe, meaning faint galaxies billions of light-years away lie superimposed on or near NGC 1277 in images. These background objects can mimic faint outer halos, making the galaxy appear more extended than it truly is. For a compact relic like NGC 1277, where the absence of an outer halo is a defining trait, correcting for background galaxies is essential. Spectroscopy brings its own challenges. When astronomers measure the velocities of stars in NGC 1277, light from nearby galaxies or intracluster gas can creep into the spectrograph's slit or fibers. This contamination can blur the velocity dispersion signal or introduce spurious features into the spectrum. Integral field spectroscopy reduces this problem by mapping multiple regions at once, but even then, careful data processing is needed to separate NGC 1277 starlight from its surroundings. The intracluster medium itself contributes contamination. Perseus is one of the brightest X-ray clusters in the sky, filled with hot plasma emitting strongly in X-rays and faintly in optical wavelengths. This diffuse light creates a background glow that astronomers must account for. Instruments sensitive to faint structures, like the Subaru telescope or Hubble, can pick up this glow and mistake it for part of NGC 1277's halo, if not corrected. In extreme cases, it could mask or mimic low surface brightness features. Scattered light from bright neighbors is another small problem. Big galaxies like NGC 1275 spread light across detectors, making long halos that reach into close areas. This scattered light can make it hard to see the faint outer structure of a small, close-together galaxy, like NGC 1277. This needs to be fixed by carefully removing the point spread function, PSF, of the telescope, which is how light spreads across the instrument. Without this fix, it's possible to get the galaxy's density wrong. To deal with all these sources of contamination, astronomers use a combination of techniques. Multi-wavelength observations are one tool. Images in different bands can reveal which light comes from stars, which from gas, and which from background galaxies. For example, Hubble's optical imaging isolates NGC 1277's stellar light, while radio and millimeter observations with ALMA confirm its lack of cold gas. Combining these data reduces the risk of mistaking contamination for genuine features. There is also the part of advanced models. Astronomers use mathematical functions to fit NGC 1277's surface brightness profile and then compare those functions to the light distribution around the star. Any extra light that doesn't fit the model can be marked as coming from nearby homes. Astronomers sometimes run models to figure out how much light close galaxies should give off, then take that amount away from the real data. These steps make sure that what's left really belongs to NGC 1277. Early predictions of NGC 1277's black hole mass were all over the place because it was hard to keep the view clean. If you make even small mistakes when you measure the center light profile or stellar speeds, it can change how much mass you think an object has by a huge amount. The question has been lessened by astronomers who have improved the way pollution is dealt with by hiding stars in the center, removing NGC 1275's halo, and blocking out objects in the background. No matter what, most people agree that the black hole is too big, but we won't know the exact numbers until the data is cleaned up well. Gravitational lensing and dynamical models applied. Scientists need more than one piece of information to be sure about something as strange as the huge black hole in NGC 1277. Being far away, observational bias, and not being sure about the model can all make it hard to see clearly. That's why this small space rock has been studied using two of the most powerful tools in modern astronomy: gravity lensing and dynamics modeling. They both check on their own to see how the galaxy's mass is spread out and to see if the giant core is real. Gravitational lensing occurs when the gravity of a massive object bends the light of more distant sources behind it. While NGC 1277 is not a strong lens like the giant ellipticals at the centers of clusters, its location inside the Perseus Cluster allows astronomers to test how its mass influences background light. Weak lensing studies, which measure subtle distortions of distant galaxies, help constrain the overall mass profile of cluster members. If NGC 1277 contained only stars and a normal black hole, its lensing signal would be modest. Instead, analyses suggest a steeper than expected central mass distribution consistent with an outsized black hole. This effect is weak and hard to measure, but it gives us a way to look into things that isn't based on stellar speeds. It's important to note that the lensing signal doesn't show any signs of a big, extended dark matter cloud. This supports the idea that NGC 1277 has an unusually low amount of dark matter. That absence makes the case stronger that the black hole controls its core mass budget. Tests of NGC 1277 structure that are based on orbits are the most direct. When you change the theories about how much mass is in stars, dark matter, and the central black hole, these models can recreate thousands of different stellar orbits within the galaxy. When the models are done, they compare their forecasts to the integral field spectroscopy velocity charts. Astronomers can find the best mix of factors that fits the data by making small changes to them over and over again. For NGC 1277, dynamical modeling consistently points to a black hole mass far above normal expectations. Even when conservative assumptions are used, such as allowing for a higher stellar mass-to-light ratio or adding a modest dark matter halo, the models still require a black hole of at least several billion suns. The best-fitting models land between 10 and 12 billion, with the upper range closer to 17 billion. Regardless of the exact figure, all scenarios confirm that the black hole is overmassive. Understanding orbital asymmetry is another important thing that comes from dynamical modeling. In many galaxies, black hole mass predictions can be off because it's not always clear how stars move, randomly, radially, or tangentially. Even though NGC 1277's models show that the orbits aren't perfectly smooth, they also show that the measured stellar speeds can't be explained without a huge black hole. One of the main complaints about the first finding is no longer valid. Scientists can lower their risk of being fooled by a single method by mixing lensing and dynamical modeling. Lensing limits the shape of the outer mass profile, and dynamics limits the shape of the central center. In NGC 1277, both types of proof come together. The galaxy is small, mostly made up of stars, doesn't have much dark matter, and is run by a black hole that is way too big for its surroundings. The fact that these ways agree makes people even more sure that the galaxy is really amazing. These approaches also highlight the uniqueness of NGC 1277 compared to its cluster peers. Other galaxies in Perseus show normal correlations between black hole mass and stellar distribution when analyzed with similar techniques. NGC 1277 alone stands out as an outlier, confirming that it is not simply an artifact of the measurement methods or the cluster environment. With the arrival of the James Webb Space Telescope, JWST, and upcoming ground-based giants like the Extremely Large Telescope, ELT, gravitational lensing and dynamical modeling will become even more powerful. JWST's infrared capabilities can probe the stellar populations of NGC 1277 with greater accuracy, tightening the constraints on its mass-to-light ratio. The ELT's adaptive optics systems will resolve stellar motions at finer scales, reducing uncertainties in velocity dispersion and orbital anisotropy. Together, these tools promise to narrow the black hole mass range and settle lingering debates. Scientists can lower their risk of being fooled by a single method by mixing lensing and dynamical modeling. Lensing limits the shape of the outer mass profile, and dynamics limits the shape of the central center. In NGC 1277, both types of proof come together. The galaxy is small, mostly made up of stars, doesn't have much dark matter, and is run by a black hole that is way too big for its surroundings. The fact that these ways agree makes people even more sure that the galaxy is really amazing. Statistical rarity of such galaxies. Not only are relic galaxies like NGC 1277 strange, they are also incredibly rare. There are very few galaxies in the local universe that meet the criteria of being small, old, and ruled by an extremely large black hole. Most galaxies, even ellipticals with about the same mass, clearly show signs of growth through mergers. These include stacked stellar populations, extended halos, and black holes with masses that are equal to those of the stars. Because of its structure that seems to have frozen in time, NGC 1277 is in a group of galaxies that studies say may only include one in every 1,000 close massive galaxies. Big scans of the sky, like the Sloan Digital Sky Survey, SDSS, and follow-up projects using Hubble and telescopes on the ground, have tried to figure out how many relics are out there. They are primarily interested in galaxies with small sizes compared to stellar mass, old stellar populations, and little to no cold gas. A huge number of galaxies have been recorded, but only a few of them meet the strict requirements. Even though NGC 1277 is still the most extreme, galaxies like MRK 1216 and NGC 1271 show that this is a real class and not just a one-off. They are mathematical outliers in every study because they are so rare. But the fact that they exist at all is enough to show that regular theories of galaxy growth are wrong. The rarity has to do with the past of the universe. Compact red nuggets were typical in the early world. Astronomers think that about half of all large galaxies were thick and close together, like NGC 1277 at redshift 2, which was about 10 billion years ago. Most of them grew into the huge ellipticals we see today over time, by merging with other ones. Only a very small number of them were able to avoid this evolutionary path, either by staying away from other objects in the cluster, or by being in lucky cluster paths that kept them from colliding. That survival rate of only a few tenths of a percent is what makes it so that there are so few relics left in the modern world. This is backed up by simulations. When you look at how thousands of galaxies have changed over billions of years, you almost always see red bits turning into giants. But the simulations also say that a very small part, usually less than 1% of the population by now, should stay the same. This statement fits with the fact that NGC 1277 and its relatives exist. They are live remains of a class that used to be common, but is now mostly extinct. The fact that they are rare doesn't make them strange. It makes them the cases that prove the rule. The scarcity of relics also affects how astronomers prioritize them. Each one is a cosmic jackpot. Because they are so uncommon, relics become targets for the most powerful telescopes and the most detailed studies. NGC 1277 alone has consumed hundreds of hours of observing time with Hubble, Keck, the Very Large Telescope, and other facilities. Future campaigns with JWST and the Extremely Large Telescope will likely revisit it again and again, because studying even a single relic can reveal more about the early universe than an entire sample of ordinary ellipticals. One more reason relics are so rare is that they have to meet a very specific set of conditions. They have to grow quickly, die off quickly, and then stay away from big mergers for billions of years. If you deal with them too much, they turn into regular ellipticals. If they don't get enough cooling, they keep making stars and lose their relic status. It's not likely that this balance will be kept in the universe. That's why NGC 1277 is both a mystery and a prize. It met all the impossible conditions to stay frozen for 10 billion years. The rarity also means that each discovery helps refine the statistics. The identification of MRK 1216, NGC 1271, and a few others confirmed that relics are not unique, but the small numbers highlight just how exceptional they are. Surveys continue to search systematically for more, especially with instruments like JWST that can detect compact ancient galaxies with unprecedented clarity. Every new relic found strengthens the case that NGC 1277 is not alone, but still part of one of the rarest galaxy populations known. JWST's role in searching for more relics. It was a new age in the search for old galaxies like NGC 1277 when the James Webb Space Telescope, JWST, was launched in 2021. Hubble had already changed the way we think about compact galaxies at high redshift, but JWST's infrared vision, wider screen, and unmatched sensitivity take the search much further. JWST is the most powerful tool ever made for scientists who want to find old galaxies in our universe and link them to galaxies that lived a long time ago. The fact that JWST can see in the infrared is one of its best features. As the universe expands, light from faraway galaxies is stretched or redshifted, and a lot of it comes to Earth in the form of infrared waves. Some of this could be seen by Hubble, but JWST is better at seeing it. So it's a great place to study the red nuggets that were around when the universe was only 2 to 3 billion years old. By bringing out the details of their shapes, JWST shows that many of them are as dense and packed as NGC 1277. Looking at NGC 1277's older friends through the telescope is like seeing them in real time. But JWST's role isn't limited to the distant universe. Its sensitivity also makes it possible to study nearby relics with unprecedented depth. In galaxies like NGC 1277, JWST can resolve the faint outer regions, measure the distribution of old stars, and search for any trace of hidden younger populations. Its instruments can also detect faint gas or dust that other telescopes might miss, helping to confirm whether relics are truly sterile or whether tiny amounts of star formation still linger. So far, NGC 1277 looks every bit the fossil it was thought to be. JWST also provides a powerful way to study stellar populations within relics. Its spectrographs can dissect the light of NGC 1277 stars to determine their ages, metallicities, and chemical histories with greater precision than ever before. This helps astronomers reconstruct the timeline of star formation, confirming that the galaxy's stars were created in a single, rapid burst more than 10 billion years ago. These details connect NGC 1277 directly to the red nuggets JWST sees at high redshift, bridging the gap between the early universe and today. The JWST is letting scientists find more ancient objects, which may be the most important thing it does. Wide-field scans with ground-based cameras find possible compact galaxies. However, high-resolution imaging and spectroscopy are needed to prove that they are indeed compact galaxies. Now, JWST is being used to keep an eye on these possible relics and see if they really do have the old stars, tight structures, and big black holes that are expected of them. Early data show that relics are indeed as rare as thought, but JWST is growing trust in the statistics by confirming more examples. Testing the role of feedback and black hole domination is another important thing that JWST does. JWST can find out how fast black holes and galaxies grew in the early universe by looking at both nearby relics and faraway red nuggets. It would be proof that this path was more common than was thought if other relics showed the same pattern as NGC 1277. Black holes that grew too big too quickly and put out their hosts. JWST has already found supermassive black holes in galaxies that formed less than 1 billion years after the Big Bang. This supports the idea that early rapid growth is possible. JWST works well with other telescopes as well. For instance, comparing JWST's stellar population data with ALMA's radio readings of gas can confirm whether relics really do not contain any material that could form stars. By resolving stellar motions at even smaller scales, pairing JWST with future giants like the Extremely Large Telescope, ELT, will also improve predictions of black holes' masses. These telescopes are working together to make a multifaceted way to study artifacts with JWST at the center. The role of black holes in quenching galaxy growth. The key to NGC 1277's frozen state is in its center, a supermassive black hole that may have decided the fate of the galaxy billions of years ago. Astronomers now think that black holes are not just inactive parts of galaxies. They are also involved in how they change over time. When a black hole gets big enough, the energy it sends out in the form of jets, winds, and radiation can change the host galaxy's surroundings in a big way. One of the main reasons galaxies stop making stars is this process, which is called feedback. It is very likely that feedback stopped the rise of NGC 1277 because of all the proof. The stars we see now were made in a very short time by a very strong explosion. Soon after, almost all star formation stopped. Since the galaxy was young and full of thick gas, this quick stop makes me think that something strong got in the way. The main suspect is the center black hole, which most likely grew very quickly in those early days. As the black hole consumed gas, it would have unleashed enormous amounts of energy. Some of this energy emerged as radiation pressure, heating and pushing surrounding gas away from the core. Other energy may have taken the form of jets, high-speed streams of particles blasting out from the black hole's poles. These processes can clear a galaxy's central regions of star-forming material and prevent new gas from cooling and collapsing into stars. Once the black hole reached billions of solar masses, it could effectively sterilize the entire system. This idea fits with what astronomers see in quasars, the luminous early universe galaxies powered by ravenous black holes. Quasars shine brilliantly for a short time as their black holes consume vast amounts of gas, then fade as the fuel runs out. NGC 1277 may once have been such a quasar, blazing in the early universe before its black hole blew away the gas supply. What remains is the aftershock, a compact fossil galaxy locked into quiescence by the very engine that once made it shine. The role of feedback also explains why NGC 1277 is so compact. In most galaxies, mergers add new gas and stars, puffing up their size over time. But in NGC 1277, the black hole feedback likely expelled gas so thoroughly that no fresh material was available, even if mergers had occurred. The lack of fuel kept the galaxy small, while the black hole continued to dominate its mass budget. Feedback froze NGC 1277 in its red nugget stage and kept it there for 10 billion years. This phenomenon isn't unique to NGC 1277. Astronomers see similar signatures in other relics and in simulations. When galaxies are quenched early by black hole feedback, they remain compact and fossilized. The difference is that most of these galaxies later grew through mergers, masking the fossil signature. NGC 1277 avoided that, leaving feedback as the smoking gun for its frozen evolution. There is still disagreement about the exact ways it works. Did the black hole stop stars from forming by making gas too hot for it to cool down? By sending it all out in huge outflows? Or by creating chaos that kept things from falling apart? Answers tend to be different in different scenarios. There was only one winner though. When the black hole reached a certain mass, the galaxy stopped growing. The future of NGC 1277. NGC 1277 is an old galaxy that has been around for a long time, but it will still be affected by the future. It has been frozen for more than 10 billion years, but it is still orbiting in the busy Perseus Cluster. Gravity, interactions, and cosmic aging will finally decide what will happen to it. It's not a question of if NGC 1277 will change, but when and how it will happen. It has an extremely quiet past, but the future could still be very exciting. The most important thing to know about NGC 1277's future right now is that it will not be able to make new stars. The galaxy cannot restart stellar birth on its own because it lacks a cold gas reserve and no signs of refilling. It's possible that the overly large black hole would heat or push out the gas from a small satellite galaxy before it could collapse into stars. As a result, NGC 1277 will keep moving around like a skeleton, with its stellar population deteriorating further and its colors turning redder as younger stars die off and only older ones survive. The long-term evolution will depend heavily on its orbit within the Perseus Cluster. If NGC 1277 stays on a relatively isolated path, as it seems to have done for billions of years, it could survive as a compact fossil for many more billions. However, if its orbit carries it too close to the cluster's center, it could be drawn into the gravitational grasp of the central giant, NGC 1275. In that case, the relic might eventually be cannibalized, its stars and black hole added to the cluster's core. This is a common fate for galaxies in dense clusters. Few survive forever. Even without a merger, the galaxy will continue to slowly lose stars over time. Gravitational interactions with other cluster members can tug at its outer layers, peeling away stars into faint tidal streams. Because NGC 1277 is already so compact, this process may not change its structure much, but over billions of years it could erode the edges of the fossil, leaving an even denser core. Though dormant today, it could still awaken under the right conditions. If NGC 1277 ever captured a gas-rich companion or wandered into a stream of intra-cluster material, its black hole could flare into activity again. Even a small amount of fuel could light it up as a low-level active galactic nucleus, producing jets or outflows. While this would not restart star formation, it could briefly alter the galaxy's appearance, reminding the cluster that the monster inside still breathes. On much longer timescales, tens of billions of years, the galaxy's stars will continue their natural evolution. Most will become white dwarfs, slowly cooling embers of their former brilliance. Some will collapse into neutron stars or black holes. Over time, NGC 1277 will become a graveyard of stellar remnants orbiting their ancient supermassive tyrant. In a far future universe, long after new star formation has ceased everywhere, galaxies like NGC 1277 will look less like living systems and more like stellar cemeteries bound by gravity. Of course, NGC 1277 could also be thrown out of the cluster completely by collisions with other galaxies. Three-body interactions between galaxies are rare, but they can send one member hurtling through intergalactic space at very high speeds. If this happened, NGC 1277 could drift through the void of space by itself forever, taking its black hole and dead stars with it. As far away from any other galaxies as possible, it would be the most interesting object ever. That's all there is to say about NGC 1277, the old galaxy ruled by a huge black hole. Enjoyed exploring one of the weirdest fossils in the universe? Like this video, subscribe to Beyond Horizons, and click the bell to make sure you don't miss our next deep dive into space. Watch the video now if you want to see more mind-bending space riddles.